What makes a magnetar more extreme than a normal neutron star? How can supermassive black holes grow into quasars? Why do magnetars and quasars reveal nature's most powerful engines? Out in the depths of space, far beyond the reach of any human touch, exist objects so extreme and strange that they challenge our understanding of nature. Imagine a place where the familiar rules seem to bend or break, where gravity and magnetism reach intensities we can scarcely imagine. In these exotic corners of the cosmos, stars can collapse into city-sized spheres with the mass of a sun, and galactic hearts can blaze with the light of 1 trillion suns. We are about to explore two of the most extraordinary phenomena the universe has to offer: magnetars and quasars, the ultimate extremes of magnetism and energy. Why do such extremes matter? In part, because they push the laws of physics to their breaking points. In the gentle darkness of a night sky, most stars twinkle with steady light, bound by the familiar forces we know. But an extreme object is different. By their very nature, magnetars and quasars operate under conditions so intense that matter and energy behave in extraordinary ways. Observing these cosmic outliers gives us a window into realms we could never recreate on Earth, a chance to witness nature at its most unrestrained and marvelous. They allow us to test our theories against the harshest environments the universe can offer. Magnetars and quasars stand at opposite ends of cosmic extremes. One is tiny yet ferociously powerful, a dense stellar corpse with a magnetic field beyond comprehension. The other is enormous and radiant, a galactic core shining brighter than whole galaxies, fueled by a supermassive black hole. As we journey through this narrative, we will gently uncover what makes these objects so extraordinary. We'll traverse the life and death of stars to find how a magnetar is born from catastrophe. We'll venture into the hearts of galaxies to see how quasars ignite. In this slow and wondrous expedition, allow yourself to drift among the stars and imagine these extremes as we explore what they are, how they form, and why they fascinate us. Let us begin at the end of a star's life. In a distant corner of our galaxy, picture a star many times more massive than the Sun, nearing the end of its fuel. Deep within its core, nuclear fires that sustained it for millions of years start to falter. Without the outward push of fusion, the core can no longer resist its own immense gravity. In a final dramatic moment, the star's core collapses inward at nearly 1/4 of the speed of light. The outer layers, no longer supported, rush in, then rebound outward in a titanic explosion, a supernova, briefly outshining an entire galaxy. What remains of the star's heart is left behind amid the wreckage, an ultra-dense ember called a neutron star. This neutron star is a cosmic cinder, small, dark, but incredibly dense. Imagine something as massive as our Sun crushed down into a sphere only about 20 kilometers across. It's as if an object the size of a city carries the weight of an entire star. On its surface, gravity is unimaginably intense. A pebble dropped from a short height would slam into the surface with truly explosive force, far beyond any impact we can recreate on Earth. The matter inside is packed so tightly that a single teaspoon of it would weigh billions of tons. Just a spoonful would outweigh a mountain. In this collapsed world of neutrons, atoms as we know them cannot survive. Nuclei are squeezed shoulder to shoulder, a dense sea of particles in the dark hush of a stellar graveyard. Newborn neutron stars start out extraordinarily hot and often spinning rapidly. Like a twirling ice skater pulling in her arms, the collapsing core spins faster and faster as it shrinks. Some neutron stars rotate dozens or even hundreds of times each second, whipping around with unbelievable speed. When a neutron star has a strong magnetic field, its rapid spin and magnetism can work together to produce beams of radiation shooting out from its magnetic poles. The star becomes a cosmic lighthouse, sweeping beams of light across the darkness. Each time a beam passes our distant viewpoint, we see a pulse. This is the phenomenon known as a pulsar, a rotating neutron star flashing on and off with clockwork rhythm as its beam sweeps by. While many neutron stars are pulsars, an even more exotic kind lurks among them, the magnetar. A magnetar is a neutron star with a magnetic field so intense it defies comprehension. Imagine magnetic forces trillions of times stronger than Earth's, then multiply that by another 1,000. In a magnetar's vicinity, atoms themselves are stretched into thin, pencil-like shapes, distorted by the ferocious field. Such power strains the star to its limits. The solid crust of a magnetar can crack under the stress, like the brittle surface of ice under immense pressure. When that crust shifts, the entwined magnetic field lines snap and realign, releasing a sudden burst of energy. In a mere fraction of a second, a magnetar can unleash more radiation than our sun emits in 100,000 years. These eruptions are fleeting cosmic blinks of astonishing power, announcing the magnetar's presence across the galaxy with a burst of high-energy light. Not every dying star leaves behind a neutron star. If the star was even more massive, the collapse does not stop at a city-sized core. Gravity presses the core further and further, until even the neutrons cannot bear the weight. The stellar remnant continues to collapse into an object of no size at all, a point of almost infinite density. A black hole is born, hidden behind a one-way boundary from which not even light can escape. In these cases, the titanic star ends its life not with a solid core, but with a gravitational abyss. This dark creation is more than just the end of a single star's story. It can become the seed of something much larger, a gravitational giant that may one day power the brightest beacons in the universe, the quasars. Now our journey shifts to the realm of giants. Deep in the hearts of most galaxies, including our own Milky Way, lurk black holes far more massive than any born in a single supernova. These are the supermassive black holes, cosmic leviathans containing millions or even billions of times the mass of our Sun. They sit in the central vaults of galaxies, often quiet, but capable of unbelievable power when awakened. One of them anchors our Milky Way, a dark mass of about 4 million suns locked away behind a veil of darkness at the galaxy's core. Yet even that is modest compared to the monsters found in distant galaxies, weighing billions of solar masses. How could such colossal black holes come into existence? Each supermassive black hole likely began as a much smaller seed in the early universe. In the cosmos's youth, conditions were ripe for the birth of these seeds. One possibility is that the very first generation of stars, forming just a few 100 million years after the Big Bang, produced a crop of extremely massive stars. These primordial giants lived short, brilliant lives, and then died in collapse, leaving behind black holes, perhaps tens or even hundreds of times the Sun's mass. Such stellar remnants could have served as the initial seeds for future supermassive black holes. Another path to a seed might not involve stars at all. In some young protogalaxies, immense clouds of gas may have collapsed directly under their own gravity, skipping the usual star formation stage. In one fell swoop, a vast gas cloud could funnel into a central black hole, forming a behemoth seed, perhaps 100,000 solar masses in size. With these early seeds, whether born from dying stars or direct collapse, the universe even in its infancy, began sprinkling the cosmos with the makings of future giants. Having a seed black hole was just the beginning. To grow from a small seed into a supermassive colossus, a black hole needed to gorge on matter and occasionally merge with its kin. In the crowded young universe, gas and dust were abundant in newly forming galaxies. A nascent black hole embedded in a rich gas cloud could swallow material relentlessly, doubling its mass again and again. Given millions of years of feasting, a black hole can swell enormously, much like a fire growing into an inferno as more fuel is added. And when galaxies collided and merged, their central black holes were drawn together in a slow gravitational dance, eventually merging into one. Each such union combined two smaller masses into a larger whole, jump-starting the growth of the black hole even further. These processes, ceaseless feeding and occasional mergers, allowed some black holes to reach astonishing sizes on surprisingly short cosmic timescales. In fact, we observe quasars, whose light began its journey when the universe was less than 1 billion years old, yet whose central black holes already weigh billions of suns. This tells us that under the right conditions, a humble seed can become a giant very quickly by cosmic standards. By the time the universe matured, most large galaxies carried a supermassive black hole in their core. Those giants would remain dormant until something roused them. When they finally fed again, they would blaze forth as quasars, the brilliant beacons we will soon explore in detail. In the cosmic theatre of extremes, power is often generated by two key ingredients: rotation and accretion. Whether in a stellar remnant or a galactic core, a spinning object and a flow of infalling matter can act like the spinning turbines and fuel of a cosmic engine. When nature sets these conditions just right, the result is an outpouring of energy on a mind-boggling scale. Both magnetars and quasars, different as they are, harness these principles, one through a rapidly spinning, magnetized star, the other through a voraciously feeding black hole. They are engines of fury, converting gravity and motion into light and radiation. Consider the case of a spinning neutron star. Its rapid rotation and intense magnetic field work together like the dynamo of a natural generator. With each turn, the star's magnetic field whips around in space, accelerating charged particles and sending out beams of electromagnetic radiation. This mechanism taps into the star's rotational energy, gradually converting the momentum of the spin into light and other radiation. Over thousands of years, a pulsar will slowly wind down as it shines, its cosmic engine losing speed while energy is carried away into the cosmos. In a magnetar, there is an additional wellspring of power: the star's magnetic field itself. The magnetic energy bottled up in and around the neutron star is so immense that its gradual decay keeps the star hot and glowing with X-rays. Even in the quiet times between violent flares, a magnetar emits a steady, restless, high-energy glow, fueled by the slow release of magnetic energy. Then, when a crack in the crust triggers a sudden rearrangement of the field, it's like a capacitor unleashing all its stored charge in one blinding instant. In that moment, the magnetar's engine releases a furious burst of radiation before subsiding back to its simmering state. Now consider the engine at the core of a quasar, an accretion disk around a supermassive black hole. As gas and dust spiral inward toward the black hole, they form a flattened disk swirling at immense speeds. This infalling matter heats up to extraordinary temperatures, millions of degrees, and begins to blaze with intense light. The accretion disk becomes a cosmic furnace, converting the force of gravity into radiant energy. A quasar's disk can outshine the combined starlight of the entire galaxy that surrounds it. From a region no larger than our solar system, it pours out torrents of radiation across the universe. The black hole itself, paradoxically dark, is encircled by this brilliant whirlpool of matter that lights up the cosmos. The swirling magnetic fields near the black hole, combined with the hole's rapid rotation, can also launch twin jets of particles from the poles of the accretion disk. These jets are like cosmic fire hoses, blasting out matter at nearly the speed of light. They drill through the galaxy and beyond, narrow shafts of plasma that can extend for tens of thousands of light years. In distant images of quasars, these jets reveal themselves as faint, radio-bright streaks shooting out of galactic cores, a sign of the ferocious energy being channeled from the heart of the quasar. Quasars don't only beam energy in tight jets, they also unleash it broadly. The intense radiation from the accretion disk can push gas outward in powerful winds, driving a cosmic storm that sweeps through the galaxy's center. The energy output is so immense that it can literally blow the gas out of the host galaxy, affecting the birth of new stars and the galaxy's evolution. It's a breathtaking thought. A black hole, famous for swallowing light and matter, can also propel vast amounts of energy back into space. All of this fury, the light of the disk, the jets, the winds, is powered by gravity drawing matter in, and often enhanced by the black hole's spin. In effect, nature has built an engine that turns the simple act of matter falling into a deep gravitational well into one of the most luminous phenomena in the universe. Behind every extreme cosmic object lies the primal force of gravity. It is gravity that sculpts neutron stars and black holes in the first place, the engine of collapse that crushes matter into mind-bending densities. In a magnetar or pulsar, gravity's inward pull holds the star together against the intense outward pressures of nuclear forces and magnetic fields. In a quasar's galactic core, gravity corrals orbiting gas and dust, holding the swirl of matter in a tight grip and drawing it inexorably toward the central black hole. The stronger the gravity, the deeper the cosmic trap. Near a black hole's event horizon, space is curved so sharply that even beams of light struggle to climb away. Matter tumbling into this abyss releases tremendous energy, much like water rushing down a waterfall, turning a turbine. Gravity is thus the fundamental power source for a quasar's brilliance. It even bends light itself, creating gravitational lenses that can distort and magnify images of objects behind the black hole. In these extreme environments, gravity provides the stage on which all other forces play their part. If gravity is the sculptor, magnetism is the artisan that carves fine details in these extreme objects. In neutron stars, magnetic fields are crucial players. A pulsar's strong magnetic field channels charged particles and shapes its lighthouse-like beams. In magnetars, the magnetic field is the dominant force near the star's surface, powerful enough to twist and stress the solid crust and to influence how radiation escapes. These fields can trap plasma in looping structures around the star and create hotspots at the magnetic poles. The magnetic force in a magnetar is so immense that it imprints itself on everything nearby, even altering the behavior of empty space and light. In such fields, atoms are stretched, and light itself can become polarized, dancing to the tune of magnetism. Magnetic fields also thread through the heart of quasars. The rotating disk of gas around a supermassive black hole winds up magnetic field lines like a giant dynamo. These fields, in turn, help launch and collimate the spectacular jets, flinging particles outward in narrow beams. Magnetism thus serves as a mediator, translating the black hole's spin and gravitational energy into outgoing flows. Within the dense disk, tangled magnetic fields stir up turbulence and help funnel gas inward, regulating how the black hole feeds. Even in a quasar's brilliant fury, magnetism organizes and channels chaos into structured outpourings of energy. From neutron stars to galactic cores, magnetic fields provide an invisible scaffold that dictates how matter and energy move in extreme environments. Lastly, there is light itself, the electromagnetic radiation pouring out of these extreme environments. Light is the messenger that carries away energy, the final product of gravity and magnetism's interplay. In a neutron star, the spinning or magnetized core loses its energy as a flood of photons, from radio waves to high-energy gamma rays, streaming into space. In a quasar, the gravitational potential energy of infalling matter is transformed into the intense glow of the accretion disk and the brilliant shine of jets. In both cases, the otherwise invisible workings of gravity and magnetism are made visible through the light they emit. Radiation is not merely a byproduct. It can exert influence of its own. The intense beam of light from a quasar's core pushes on the surrounding gas. This radiation pressure can counteract gravity's inward pull. Indeed, many quasars radiate at a level where the outward push of light nearly balances the inward drag of gravity, a cosmic tug-of-war that naturally regulates how brightly the quasar can shine. In the densest accretion flows, if too much matter tries to fall in at once, the resulting blaze of radiation will blow some of it back, preventing the black hole from consuming matter faster than nature allows. Light also carries information. Across the spectrum, from radio waves with their low-frequency whisper to energetic X-rays and gamma rays, electromagnetic radiation encodes clues about these extreme realms. The color and intensity of the light, its spectrum, and even its polarization reveal conditions like temperature, composition, and magnetic fields. Without light, and its invisible kin like X-rays and radio waves, magnetars and quasars would lurk unseen. But thanks to light, these cosmic beasts announce themselves across vast distances, allowing us to witness the otherwise hidden drama of extreme gravity and magnetism from the safety of Earth. How can we know so much about places we can never visit? The answer lies in decoding the signals that these cosmic powerhouses send us. Across the vast gulf of space, magnetars and quasars announce themselves with pulses of radiation, shifting spectral patterns, and other subtle clues. Astronomers have become adept at reading these clues, like detectives piecing together a mystery. Every photon, every particle, every fleeting vibration of space-time that reaches Earth carries a message about its extraordinary source. We have learned to listen to the rhythm of pulsars, to spread out the light of quasars into rainbows of information, and even to detect invisible ripples in space itself. Together, these techniques allow us to understand magnetars and quasars without ever leaving our planet. One of the astronomer's most powerful tools is spectroscopy, splitting an object's light into its constituent colors to reveal hidden details. In the early 1960s, a seemingly star-like object in the sky baffled scientists with its peculiar spectrum. When its faint light was spread into a rainbow, it showed familiar fingerprints of hydrogen, but shifted so far from their usual positions that they were initially unrecognizable. Eventually, it dawned on researchers that these lines were enormously redshifted, stretched to longer wavelengths by the expansion of the universe. This meant the object was located billions of light-years away, and yet appeared star-like in a telescope, implying an almost unimaginable brightness. That discovery marked the identification of the first quasar. By decoding its light, astronomers realized they were witnessing the glow of matter swirling around a supermassive black hole in a distant galaxy. Since that breakthrough, spectroscopy has been a key method for understanding extreme objects. Every chemical element leaves a unique pattern of lines in a spectrum, allowing us to identify what an object is made of. The spread of colors also tells us about temperature and motion. Gas moving toward or away shifts the lines, a Doppler effect, and turbulent or fast-orbiting gas broadens them. For quasars, we see broad emission lines from gas whipping around at thousands of kilometers per second, direct evidence of a black hole's gravitational grip. For magnetars, we examine their X-ray spectra for clues about surface conditions. Certain subtle features might hint at the influence of the intense magnetic field on the escaping radiation. By reading the spectral code hidden in light, we glean a wealth of information: composition, temperature, velocities, and more, all without leaving our observatories. Another vital clue comes from timing, the study of how an object's emission changes over time. In 1967, a young astronomer named Jocelyn Bell noticed a peculiar signal in her radio data, a series of pulses arriving with metronome regularity every few seconds. At first, this strange beacon was nicknamed Little Green Men because no natural explanation seemed to fit. Soon, scientists realized it was not aliens at all, but a rapidly spinning neutron star, flashing its beam toward Earth with each rotation, a pulsar. This was the first direct evidence of a neutron star's existence. By measuring the interval between pulses, astronomers can determine the star's rotation period with incredible precision. Some pulsars rotate astonishingly fast, spinning hundreds of times each second, whereas magnetars and other neutron stars spin more slowly, often once every few seconds. Precise timing of these cosmic clocks lets us peer into their interiors. If a pulsar's rhythm falters or glitches slightly, it can indicate a starquake in a magnetar's crust or other internal changes. Over years, we also observe pulsars gradually slowing down as they lose energy, which beautifully confirms that their emitted radiation is draining their rotational energy. Timing the beats of pulsars and magnetars has thus become a window into the unseen mechanics of these dense stars. Quasars, for their part, do not blink on and off like pulsars, but they do vary over time. By monitoring a quasar's brightness over months and years, astronomers notice gradual flickers and flares. These changes carry information. If a quasar's light output rises or falls significantly in, say, a few days, then the region producing that light cannot be larger than a few light days across. Otherwise, different parts would smooth out the change. Such timing clues reveal that the quasar's energy source is confined to a relatively small space, reinforcing the idea of a compact accretion disk around a central black hole. Thus, even the variability of quasars becomes a tool, allowing us to estimate the size of their inner regions and to understand the dynamics of their central engines. Another subtle clue comes from the polarization of light. Light waves oscillate, and this oscillation can have a preferred direction. Much as glare from water or glass can be filtered by polarized sunglasses that block certain orientations of light, astronomers measure the polarization of light from distant objects to learn about the environments the light has passed through or originated in. Polarized radio waves from pulsars and nebulae, for example, reveal that their radiation is produced by electrons spiraling in magnetic fields, a process known as synchrotron emission. In quasars, light scattered by dust or emitted from magnetized regions of the disk and jets often arrives with a telltale polarization. These signatures let us infer the orientation and strength of magnetic fields in those far-off central engines. Even magnetars offer clues. Their intense magnetic fields can impart distinctive polarization patterns to X-rays, providing a rare test of physics in ultra-strong fields. By studying the direction in which light waves prefer to vibrate, polarization measurements allow us to peek at otherwise invisible magnetic architectures and scattering processes in these extreme environments. In the last decade, astronomy has opened new eyes and ears on the cosmos. We no longer rely on electromagnetic waves alone. We can now detect elusive messengers like gravitational waves and neutrinos. In 2017, detectors on Earth felt the tiny ripple of spacetime from two neutron stars spiraling together and merging. This gravitational wave signal, a faint rising chirp in the fabric of space, was soon followed by a burst of gamma rays and a glow of debris seen by telescopes. Together, these observations confirmed that colliding neutron stars produce brilliant explosions and forge heavy elements like gold. It was a stunning demonstration of multi-messenger astronomy, hearing a cosmic event through gravity and seeing it in light. Astronomers are also catching high-energy neutrinos, nearly massless, ghostly particles, arriving from cosmic sources. In one instance, a single neutrino detected in an Antarctic observatory was traced back to a distant flaring galaxy with a supermassive black hole. This suggested that the quasar's jet was accelerating particles to incredible energies, producing neutrinos and cosmic rays. For the first time, scientists had direct evidence linking a neutrino to a quasar, proving that these cosmic beacons indeed double as immense particle accelerators. By combining all these messengers, light across all wavelengths, gravitational waves, neutrinos, and perhaps others yet to be detected, we can paint a far richer picture of magnetars and quasars. Each type of signal carries unique information. Together, they tell a more complete story of what is happening in and around these extreme objects. Multi-messenger observations are allowing us to see these cosmic phenomena with new clarity, bringing their once hidden details into sharper focus. Armed with this wealth of observational insight, astronomers have been able to piece together the family tree of extreme cosmic objects. Magnetars, pulsars, black holes, quasars. Each is a unique entity, yet they are interrelated members of a grander cosmic menagerie. To truly appreciate how special magnetars and quasars are, it helps to compare them side by side with their kindred extremes. On the neutron star side, magnetars and pulsars are essentially siblings. Both are neutron stars, born from the collapsed core of a massive star and sharing the same tiny scale, only about 20 kilometers across, the size of a city. They are ultra-dense spheres left in the aftermath of supernova explosions. What differentiates a magnetar from a common pulsar is its behavior and energy source. A pulsar spins rapidly, some whirl hundreds of times per second, and emits regular pulses of radio waves or light, like a lighthouse, powered by its rotational energy. A magnetar, by contrast, often rotates more slowly, once every few seconds, but boasts a magnetic field hundreds of times stronger than that of a typical pulsar. This intense magnetism can twist the star's crust and unleash sporadic, violent flares. Pulsars tend to be steady timekeepers, blinking reliably with each rotation, whereas magnetars are more like sleeping dragons, mostly inert, but prone to occasional outbursts when their magnetic stress becomes too much. In essence, they are two faces of the neutron star family, one defined by extreme rotation, the other by extreme magnetism. Intriguingly, they may not be entirely separate categories. A neutron star could be born as a magnetar, and then, as its magnetic field decays over thousands of years, settle into a quieter life, more like a typical pulsar. These stellar remnants are connected by their common origin and nature, yet exhibit strikingly different personalities under different conditions. Black holes, too, come in different sizes and contexts. A stellar mass black hole, formed from the collapse of a very massive star, might contain a few times the Sun's mass. In contrast, the supermassive black holes at galactic centers hold millions to billions of solar masses. Yet, in a sense, they are the same type of object, differing only in scale. To put it in perspective, a black hole 10 times the Sun's mass has an event horizon of only around 60 kilometers in radius, whereas a billion solar mass black hole boasts an event horizon as large as our entire solar system. Both are absolute traps from which nothing, not even light, can escape once past that boundary. The supermassive beast is simply a far larger gravity well, one that can swallow stars and vast quantities of gas whole. Astronomers have also found black holes of intermediate mass, hundreds or thousands of suns, which likely form through the merger of stars or smaller black holes. These medium-sized black holes bridge the gap between their stellar-sized and supermassive kin. Whether big or small, a black hole's visibility depends on its diet. A lone black hole drifting through space is essentially invisible, emitting no light of its own. We can only detect such a quiet black hole by its gravitational effects on nearby stars or gas. But if a black hole has material to feed on, it can become a beacon. In our Milky Way, for example, some stellar mass black holes reside in binary systems with normal stars. Gas from the companion star spirals toward the black hole, forming a scorching accretion disk that emits intense X-rays. Sometimes, the infalling gas triggers the launch of small jets. Astronomers call these systems micro-quasars, miniature quasar-like objects, because they mimic, on a much smaller scale, the disk and jet spectacle of a quasar. Likewise, most supermassive black holes sit quietly at their galactic centers until fuel is available. When a fresh supply of gas funnels into a galaxy's core, the sleeping giant awakens. The black hole devours matter and flares into a quasar, or a related active galactic nucleus. During this active phase, it blazes brilliantly, but once the feast is over, when the fuel is exhausted or expelled, the quasar fades and the black hole goes dormant again. In this way, magnetars and quasars can be seen as analogous in their families. A magnetar is a neutron star in an active, highly energetic state, and a quasar is a supermassive black hole in an active feeding frenzy. Comparing these extreme objects side by side highlights how nature pushes the limits in different ways. Magnetars embody the frontier of matter and magnetism. They cram a sun's worth of mass into a sphere the size of a city and wield magnetic fields that defy our earthly experience. In them, we find a laboratory for nuclear matter under crushing density and for quantum processes in ultra-strong magnetic fields. Quasars, by contrast, represent the extreme of gravity and luminous energy on a galactic scale. They warp space-time around gargantuan black holes and radiate with the power of entire galaxies. Through magnetars, we probe the microphysics of how matter and light behave under conditions of immense density and magnetism. Through quasars, we explore the macrophysics of gravity, witnessing how a black hole can influence an entire galaxy and drive some of the brightest phenomena in the universe. By studying both, scientists inch toward a more unified understanding of nature's fundamental forces, from the quantum to the cosmic. Though disparate in scale and form, each of these exotic objects illuminates a different aspect of the grand tapestry of physics. In the cosmic zoo of extremes, magnetars and quasars stand out as two of the most captivating creatures, demonstrating how marvelously diverse the universe's expressions of its laws can be. Our exploration of magnetars and quasars is just one chapter in the ongoing quest to understand the universe. Many mysteries remain unsolved. What is the precise nature of matter at a neutron star's core? How exactly do supermassive black holes form so quickly in the early universe? Do magnetars truly cause enigmatic fast radio bursts across the cosmos? What happens at the very edge of a black hole's event horizon, where space and time themselves are twisted? These questions remind us that there is still so much to learn about these extremes. Each discovery we make tends to open up new puzzles, drawing us further into the cosmic depths. The roadmap ahead is as exciting as it is challenging. New observatories are on the horizon that will extend our senses further into the dark. Next-generation X-ray and radio telescopes will seek out more magnetars in our galaxy and beyond, catching their bursts and probing their magnetic fields in unprecedented detail. Advanced gravitational wave detectors are also being planned. They will be sensitive enough to listen for collisions involving neutron stars and even the mergers of supermassive black holes when galaxies collide. One day, we may hear the death spiral of a star being swallowed by a black hole, or detect the subtle tremor of a magnetar forming in a distant supernova. Each new messenger we capture will add to our understanding of how these extreme objects behave. Already, the Event Horizon Telescope has given us our first glimpse of a black hole's silhouette, capturing a ring of light around the shadow of the supermassive black hole in galaxy M87. In the near future, even sharper instruments are being designed to image black holes and their surroundings with unprecedented clarity, perhaps revealing, in detail, the swirling magnetic fields and turbulent plasma around an actively feeding black hole. At the same time, powerful new eyes, like the James Webb Space Telescope, are peering back to the era of the first quasars. They aim to observe the birth of those early giants that lit up young galaxies only a few 100 million years after the Big Bang, shedding light on how supermassive black holes came to be. Quasars were far more common in the early universe than they are now. As galaxies matured and their reservoirs of cold gas dwindled, most supermassive black holes went quiet. Today, quasars are rarer, and our own galaxy's central black hole is a dormant giant, biding its time until perhaps one day it finds new fuel. In the extremely distant future, long after the last stars have burned out, neutron stars like pulsars and magnetars will have cooled and gone dark. Black holes, however, will linger as some of the final bastions of mass and energy. One can imagine a time trillions of years from now when only black holes remain, slowly evaporating via Hawking radiation, the final faint whispers of an aging universe. Thus, when we contemplate magnetars and quasars, we connect the very dawn of creation with newborn neutron stars and early quasars to the universe's far twilight, when only fading remnants persist. The extremes of today are entwined with the cosmic story from its bright beginning to its quiet end. For now, our journey through the realms of magnetars and quasars comes to a gentle pause. We have traversed the depths of stars and the hearts of galaxies, encountering magnetic fury and gravitational splendor. But the cosmos is vast, with wonders far beyond these. As we drift away from this chapter of extremes, we carry a sense of awe and humility. The universe has shown us a few of its most intense creations, yet it surely holds more secrets in the darkness, waiting for curious minds to uncover. In this never-ending voyage of discovery, Each answer spawns new questions, and each mystery solved lights the way to the next. The cosmic night remains, but with every exploration, we illuminate a bit more of the path ahead. Our adventure is not over. It has only just begun. The stars, and whatever lies beyond them, will guide us onward into the great cosmic ocean. The life of a magnetar begins in the fiery death of a massive star. In its final moments, a star, many times heavier than our sun, exhausts its fuel and can no longer support itself against the pull of gravity. The core collapses in an instant, crushed to nuclear densities as the outer layers explode outward in a supernova. What remains at the center is a newborn neutron star, an ultra-dense ember no larger than a city, yet packing more mass than our sun. In this tiny sphere, matter is compressed so tightly that a single spoonful would weigh billions of tons. It is a piece of a star squeezed down to the weight of a mountain, a place where atoms themselves cannot survive intact under the crushing density and gravity. This infant neutron star, only seconds old, is an extreme environment, unlike anything else. It is born seething with energy, roaring hot and rapidly spinning from the violence of the collapse. Like an ice skater pulling in their arms, the collapsing core spins faster and faster as it shrinks. A star that may have rotated once every few days can end up rotating hundreds of times each second as a neutron star. In these first moments, the interior churns with convective motion, a rolling sea of subatomic particles and nuclear fluid. This furious motion, coupled with the rapid spin, sets the stage for a powerful cosmic dynamo, a mechanism that can take the newborn star's magnetic field and amplify it to extraordinary levels. Deep in the core, conducting fluids of neutrons and protons swirl and shear, twisting any magnetic field lines threading through them. The process is chaotic, but immensely effective. In mere seconds, this dynamo action can wind up the magnetic field again and again, much as a small initial field can be wound into a tight bundle of magnetic energy. The faster the rotation and the more turbulent the motion, the stronger the amplification. If conditions are just right, the field strength skyrockets to levels utterly unachievable under normal circumstances. What might have been an ordinary neutron star with a strong but unremarkable magnetic field is transformed into a magnetic monster, a magnetar. Not every neutron star undergoes this extreme transformation. Most nascent neutron stars have robust magnetic fields, perhaps 1 trillion times Earth's field, and these become the typical radio pulsars. But a select few, maybe 1 in 10, or even rarer, are born with the perfect storm of factors: rapid initial spin and intense internal turbulence. In these special newborns, the dynamo mechanism runs rampant, amplifying the magnetic field by orders of magnitude. The numbers defy easy comprehension. The field of a magnetar can reach 1,000,000 billion times stronger than Earth's. That is 10^15 Gauss, a quadrillion times the magnetism we experience on our planet. In essence, the core collapse has forged a magnetic titan in the span of a heartbeat. For a brief time right after the supernova, the newborn magnetar is like a cosmic forge, its interior generating magnetic fields as iron is forged deep inside a star's core. The nascent field threads throughout the neutron star, linking the solid crust to the liquid core like invisible steel cables under unimaginable tension. Some theories suggest that even material falling back onto the neutron star after the explosion can spin it up further, driving the dynamo process to even greater extremes. All the while, the clock is ticking fast. Only a few seconds after the collapse begins, this magnetic creation process reaches its peak and starts to stabilize. As the whirlwind of formation settles and the newborn star cools slightly, we can imagine the scene. In the heart of the still expanding supernova remnant, barely visible amid the glowing debris, there lurks a tiny object spinning madly and blazing with residual heat. Invisible magnetic force lines unfurl from it in all directions, stretching far into space. A magnetar stands revealed, a city-sized neutron star with a magnetic field so powerful that it will dominate every aspect of the star's behavior from this point forward. In the silence after the explosion, the magnetar's rapid rotation gradually begins to slow, but its magnetic field remains frozen in place. The star that died has given birth to something new and formidable. This magnetar is young, energetic, and highly magnetized, the outcome of nature's most extreme dynamo. It is the heart of magnetism incarnate, ready to unleash its power in ways we are only beginning to understand. The journey of this magnetar has just begun, and its intense field will soon make its presence known through exotic behaviors unique to such extreme conditions. If we could voyage down to the surface of a magnetar, we would enter a realm of truly extraordinary matter. The outermost layers form a solid crust of ultra-dense material, likely a crystalline lattice of atomic nuclei crushed together. Under gravity, billions of times stronger than Earth's, this solid crust is as hard as steel, perhaps far harder. It must be, to withstand the intense forces at play. Even so, the crust is under unimaginable stress from the magnetar's own gravity and magnetic field. It is only a kilometer or so thick, but it supports the tremendous weight of the entire star above it. In this environment, ordinary atoms cannot survive in their usual form. Their electron clouds are squashed by pressure and magnetic force. At the magnetar's surface, atoms become distorted into elongated shapes, compressed and stretched by fields and gravity until they barely resemble the atoms we know. Beneath the thin crust lies the vast bulk of the magnetar's interior, the core, a sphere of nuclear matter packed to densities that defy belief. Here, matter has been squeezed beyond the limits of normal atomic structure. Nuclei dissolve into a sea of subatomic particles. Protons and neutrons jostle shoulder to shoulder, and many neutrons wander freely, no longer confined to individual atoms. The core of a magnetar is like an immense atomic nucleus the size of a city, containing more mass than the Sun. In these depths, quantum physics dominates. The neutrons pair up in ways analogous to electrons in a superconductor, forming a superfluid, a bizarre state of matter that flows without resistance. Likewise, the minority of protons in the core may become a superconducting fluid, allowing electric currents to flow forever without losing energy. The entire core is a kind of giant, unearthly liquid, one that can carry currents and sound waves in ways no normal material can. It is also remarkably stiff. If you were to strike the core, vibrations would race through it, almost undamped. This is a star-sized drop of nuclear fluid, and it challenges the boundaries of what we understand about matter. At the boundary between the rigid crust and the liquid core, strange structures may form. The immense pressures create exotic configurations with whimsical nicknames like nuclear pasta, where matter arranges itself into sheets, strands, and blobs on the subatomic scale. This is nature's way of bridging the orderly crystal lattice of the crust with the chaotic particle soup of the core. The magnetar's magnetic field threads through all these layers, binding the crust and core together. Magnetic field lines anchor into the solid crust. So as the star rotates and the field shifts, it drags on the crust. The core, in turn, is coupled to the crust partly through this magnetic tether, and partly through other forces of friction and electricity. Despite the fluid interior, the magnetar's crust and core largely move as one, locked together by magnetism. Yet this unity is not absolute. Under enough stress, the crust can slip or crack, a dramatic event we will soon explore. Still, most of the time the crust and core stay in step, spinning together under the guiding hand of the magnetic field. While the interior of a magnetar is astonishing, the space just outside it is equally strange. The magnetar's magnetic field extends far outward into what would normally be the vacuum of space. But near the star, that vacuum is profoundly altered by the intense field. The empty space around the magnetar teems with fleeting particles and fierce electromagnetic forces. Quantum theory predicts that in a magnetic field as intense as this, even empty space behaves like a prism or a lens. Light travelling near the magnetar can split into different polarization modes, as if space itself has taken on a crystalline property. A beam of radiation leaving the surface may be rotated or divided by this polarized vacuum, an effect known as vacuum birefringence. In essence, the magnetar's magnetic might is so extreme that it imprints itself on empty space, making light itself dance to its tune. The magnetic field is strong enough to rip electrons from atoms and even conjure particles out of nothingness. Close to the magnetar, any stray atom or molecule would be torn apart, electrons wrenched away from nuclei by forces beyond any chemical bond. The field can imbue vacuum fluctuations with energy, spawning real particles of matter and antimatter that briefly flicker into existence. The space around the magnetar likely crackles with these electrons and positrons, forming a tenuous plasma that is corralled by the magnetic field lines. This magnetosphere, the region of space dominated by the magnetar's magnetism, is anything but empty. It is a dynamic arena where charged particles spiral along magnetic arcs, sometimes colliding and emitting flashes of high-energy light. Here, exotic quantum effects are commonplace. A single photon might transform into a pair of particles, and electrons race in tight coils dictated by the field. To a distant observer, much of this activity is invisible, but its influence is profound. The magnetar's surroundings brim with a ghostly radiance and subtle signals that only sensitive instruments can detect, such as highly polarized X-rays, carrying the fingerprint of the star's magnetic dominion. Everything about a magnetar, from its iron-hard crust and superfluid core to the altered vacuum beyond, is marked by extremes. Gravity, density, and magnetism all push physical law to its limits. In this compact object, realms of nuclear physics and quantum electrodynamics intersect in spectacular fashion. It is a place where human intuition fails. Only the language of advanced physics can truly describe what transpires inside, yet even without equations, we can grasp the wonder of it. This is matter at its most compressed, and magnetism at its most intense, coexisting in a tiny but immensely powerful star. The very existence of a magnetar challenges our understanding. It serves as a natural laboratory for phenomena we could never recreate on Earth. In the face of such extremes, we stand like spectators at the edge of an abyss, peering into a domain where the familiar rules of matter and light give way to something profoundly new and astonishing. On a quiet day, a magnetar might seem innocuous, a silent, spinning star cinder deep in space. But beneath that silence, enormous tensions can build. Over years and decades, the magnetar's ultra-strong magnetic field slowly warps and stresses the solid crust that encases the star. The crust is not a static shell. It is laced with magnetic field lines and essentially anchored to them. As the magnetic field gradually shifts or twists, it drags on the crust, imparting tremendous strain. Imagine tectonic plates on Earth building pressure along a fault line, except here the plates are pieces of a star's crust, and the force trying to move them is an unimaginable magnetic tension. Eventually, something has to give. When the crust can no longer bear the stress, it ruptures in a sudden, violent slip, a starquake. In that brief instant of a starquake, the magnetar's crust might shift by only a millimeter, but the energy unleashed is colossal. A crack racing through the dense crust sends a shudder through the entire star, like a ringing bell. This movement is enough to release magnetic energy in an instant. The crust, snapping and rebounding, heats up and even partially vaporizes. The region near the rupture can be flash heated to billions of degrees, releasing a burst of high-energy radiation. At the same time, the magnetic field suddenly reconfigures and unleashes additional energy. The result is a brilliant flare of X-rays and gamma rays, a magnetar firework that outshines entire star systems for a brief time. Astronomers first detected such bursts in the late 1970s and early 1980s. Mysterious flashes of gamma rays were seen coming repeatedly from the same spots in the sky, earning these objects the name soft gamma repeaters. Decades later, scientists realized these were magnetars revealing their true power. Most of the time, these bursts are relatively short and moderate by cosmic standards, perhaps lasting a fraction of a second, releasing as much energy as our sun emits in a year. These are the minor tremors of the magnetar world, often occurring in clusters or storms. A magnetar might fire off dozens or even hundreds of such bursts over days or weeks during an active episode. Each burst is like a release valve, relieving some stress in the crust and field. Between bursts, the star may quiet down again for years or even centuries, slowly accumulating stress once more. Every so often, however, a magnetar unleashes a far more dramatic outburst, a giant flare. These colossal eruptions are the true monsters of magnetar activity. In a giant flare, the magnetar's energy output momentarily defies imagination. For a few tenths of a second, a magnetar can emit more energy than our sun produces in 100,000 years. The flash is so intense that even across vast distances, it can affect other stars and planets. One famous example occurred on December 27, 2004, when a magnetar in the outer Milky Way, some 50,000 light-years from Earth, let loose the brightest blast of gamma rays ever recorded from beyond our solar system. In that split second, detectors on multiple spacecraft were blinded or overwhelmed by the flood of energy. The magnetar announced itself by overpowering instruments designed to observe explosions billions of light-years away. The initial spike of the 2004 flare lasted less than a second, but it was followed by a fading afterglow of X-rays that persisted for minutes. As the magnetar rotated, this X-ray fireball brightened and dimmed rhythmically, like a lighthouse beam sweeping past. With a period of 7.5 seconds, the stars spin. Meanwhile, on Earth, the effects of that distant flare were subtle but real. Our upper atmosphere was momentarily ionized by the surge of high-energy light, and Earth's magnetic field quivered faintly from the blast. It was as if our planet's defenses felt a brief, gentle tap from an event halfway across the galaxy. Such giant flares are exceedingly rare. In the past half-century, only a few have ever been recorded. The first was observed in March 1979 as an enigmatic gamma-ray flash. Another followed in 1998, and then the 2004 superflare that shattered records. Each of these events heralded a magnetar pushing its crust and field to the breaking point. After a giant flare, the magnetar usually settles down again. Its rotation may slow just a bit, and its magnetic field may slightly realign, but the star survives, scarred perhaps by the violence of its own outburst. On smaller scales, magnetars frequently produce lesser bursts as well, short X-ray flashes that are far more common than giant flares. In one episode, a magnetar was observed firing hundreds of bursts over the span of a few hours, a veritable storm of high-energy flashes. During such an outburst, the magnetar can emit more total energy in a day than the sun emits in many years. X-ray telescopes have even captured expanding rings of light around some magnetars after these bursts, formed as X-rays scatter off dust clouds in space, like ripples in a cosmic pond echoing the flare across the galaxy. Such sights offer a visual echo of the magnetar's fury, even though the bursts themselves last mere milliseconds or seconds. Crucially, the radiation from magnetar flares carries clues about the star's interior. In a few cases, astronomers have detected subtle oscillations in the X-ray glow following a giant flare, vibrations that likely represent the star itself, ringing like a bell after the quake. These oscillations, imprinted on the fading X-ray tail, suggest that the crust and core were briefly set trembling together. By studying these cosmic ringing tones, scientists hope to learn about the density and composition of matter deep inside the magnetar, using the flare as a probe of the star's hidden heart. Starquakes and flares demonstrate the tremendous might hidden in a magnetar's magnetic field. Energy built up over years can be released in milliseconds, converting magnetic strain into searing radiation. These outbursts can briefly make a magnetar one of the brightest X-ray sources in the sky. Yet for all their power, flares are only one phase of a magnetar's life. After a flare, the star returns to a quiet state. The crust resettles, and the magnetic field relaxes into a new equilibrium. From afar, the magnetar goes back to being a faint, unremarkable pinpoint of X-rays. But beneath that calm exterior, the magnetic heart still beats, and in time it may erupt again. Magnetars may not only light up their own remnants, they could also energize some of the most spectacular explosions in the universe. It's suggested that newborn magnetars serve as hidden engines behind certain supernovae and even some gamma-ray bursts. These extreme explosions, often called hypernovae or superluminous supernovae, shine far brighter than ordinary stellar deaths. They are cosmic fireworks, outshining entire galaxies for weeks. The source of their vast energy has been a puzzle. Radioactive elements forged in the explosion can make a supernova glow, but in these events, the light is too intense to be explained by radioactivity alone. Something else must be pumping energy into the blast. A rapidly spinning magnetar born in the heart of the explosion is a compelling candidate. When a massive star's core collapses into a magnetar, the newborn neutron star may rotate astonishingly fast, on the order of a few milliseconds per spin, with an enormous magnetic field. If this magnetar remains intact, instead of collapsing into a black hole, it will start shedding its rotational energy. Within weeks, it can inject huge amounts of energy into the supernova debris via its magnetic winds and radiation. In effect, the magnetar becomes a central power source, pouring energy into the expanding stellar ashes. This additional input heats and accelerates the ejector, making the explosion brighter than it would otherwise be. There is growing evidence that the magnetar engine scenario happens in nature. A class of explosions, known as superluminous supernovae, have light curves that align well with magnetar-powered models. These supernovae reach peak luminosities tens or even hundreds of times higher than normal, and then fade slowly, often showing a plateau or secondary bump that hints at continuing energy injection. Fitting their light curves with magnetar models lets scientists estimate the magnetar's initial spin and field. In many cases, the required parameters are extreme but plausible. A spin of a few milliseconds and a magnetic field well above 10 or 14 Gauss. It seems likely that behind the exceptional brightness of these events lies a tiny, rapidly spinning magnetar, pumping energy into the explosion. Magnetars have also been proposed as central engines for certain gamma-ray bursts, GRBs. Gamma-ray bursts are among the most intense explosions in the universe, fleeting flashes of gamma rays lasting from milliseconds to minutes. The standard model for long-duration GRBs involves a massive star's core collapsing into a black hole that drives relativistic jets. But in a variant of this model, the collapsing core forms a magnetar instead. In this scenario, the magnetar's rapid spin and strong magnetic field launch and sustain the jets that produce the GRB. The magnetar might eventually collapse into a black hole as it loses energy, but during its brief life, it can serve as the engine powering the GRB and possibly inject energy into the accompanying supernova. This idea gained traction because some GRBs exhibit features that a magnetar could explain. For instance, a few GRBs have an extended X-ray plateau in their afterglow. The brightness stays nearly constant for tens of minutes before finally dropping off. This plateau could naturally occur if a magnetar keeps pumping energy into the explosion for a time, supporting the afterglow, until it exhausts its spin energy and then the emission fades rapidly. Another clue is the sheer energy involved in some GRBs and their supernovae. A magnetar with an initial spin of just 1 to 2 milliseconds carries an enormous rotational energy, around 10 Rs 52 ergs. Even if only a fraction of that energy is transferred to the GRB's jets and the supernova, it could account for the extreme brightness observed. The term hypernova itself arose in the late 1990s, when a remarkably energetic supernova, SN 1998BW, was observed in coincidence with a GRB 980425. The classical explanation invoked a black hole and jets to drive the event. But a magnetar engine is an appealing alternative for cases like this. If a magnetar is born during the collapse, it could simultaneously drive the GRB's jets, if jets form, and later energize the supernova's ejector. The outcome would be multi-wavelength fireworks, a blast of gamma rays from the jets, and a supernova shining unusually bright for an unusually long time thanks to the magnetar. Indeed, some of the brightest supernovae on record, which show no clear evidence of jet-driven explosions, might be powered solely by a magnetar pumping energy from within. It is likely that not every hyperenergetic supernova, or GRB, requires a magnetar. Some will indeed be powered by black holes or other mechanisms. But the magnetar engine hypothesis has added a powerful piece to the puzzle of these cosmic blasts. It shows how the death of a star and the birth of a magnetar could be entwined in a spectacular display. In a sense, the magnetar's formation can provide an extra encore to the supernova. The initial explosion is the opening act, and the magnetar's spin-down energy provides the grand finale, keeping the debris glowing far longer and brighter than it otherwise would. As our ability to observe distant explosions improves, we are gathering more data to test these ideas. Upcoming telescopes and surveys will discover more superluminous supernovae and may catch telltale signs of magnetar involvement. Perhaps peculiar bumps in their light curves or other central engine signals. We may also find additional clues in GRB afterglows, pointing to a magnetar's lingering influence. Each new cosmic explosion observed gives astronomers a chance to check if a magnetar might be lurking at its center. So far, evidence is mounting that, in some cases, these magnetic neutron stars serve as engines for cosmic pyrotechnics, turning a dramatic star death into an even more extravagant show leaving a lasting mark on the cosmos. No magnetar stays a wild, eruptive powerhouse forever. Time is the great tamer of even the strongest magnetic fields. As a magnetar ages, its magnetic field gradually decays and its frenetic activity subsides. After a few tens of thousands of years, the internal dynamo that fueled its outbursts begins to falter. The crust has released much of its built-up stress, the field has weakened from its peak strength, and the magnetar's behavior starts to change. In essence, a magnetar enters a quieter middle age, transitioning toward a calmer state, more akin to an ordinary neutron star. One of the key processes driving this change is magnetic field decay. Inside the magnetar's crust, currents that support the enormous magnetic field slowly dissipate. The extreme conductivity of neutron star matter means the decay is not rapid on human timescales, but over thousands to hundreds of thousands of years, the field can drop by a significant factor. As the field decays, the magnetar's X-ray brightness, powered largely by magnetic energy leaking out as heat, also diminishes. The star cools and dims, and its once frequent outbursts cease. What remains is a neutron star that, while still highly magnetic by normal standards, is far less volatile than it was in its youth. In this slow transformation, a magnetar may pass through intermediate stages that blur the line between magnetar and ordinary pulsar. Astronomers have identified a few high magnetic field pulsars, neutron stars with fields just below typical magnetar strength, around 10 or 13 or 10 or 14 Gauss. They generally behave like normal pulsars, yet occasionally they exhibit bursts or X-ray flares reminiscent of magnetars. Conversely, some so-called low-field magnetars have inferred field strengths closer to pulsars, indicating they could be magnetars in advanced old age whose mighty fields have waned. These in-between objects suggest that magnetars and pulsars are not entirely separate classes, but rather points along a continuum in neutron star evolution. Eventually, a magnetar might become almost indistinguishable from an ordinary, quiet neutron star. With its field reduced and its spin slowed, it would no longer produce significant bursts or high-energy emission. Its emission would be dominated by whatever residual heat it has left, perhaps detectable only as a faint, soft X-ray glow, or not at all. In this late phase, the once fearsome magnetar is an expired magnetar, a neutron star with a still strong but no longer catastrophic magnetic field and a slow rotation of maybe several seconds. It might manifest as an X-ray dim, isolated neutron star, the kind of object that merely glows softly with leftover heat and has no dramatic activity. The long, quiet tail of the magnetar's life has set in. These long, quiet tails are not just theoretical. We likely are observing them today in our galaxy. The so-called Magnificent Seven, a group of nearby isolated neutron stars that emit only steady thermal X-rays, could be examples of elderly magnetars or high-field pulsars that have shed their former fury. They have strong fields, around 10^13 Gauss, and no radio emission, and they align with what we expect of magnetars that have gone dormant. Their existence hints that many magnetars simply fade into unremarkable neutron stars over time, contributing to the grand population of cooling stellar remnants without fanfare. In its fading years, a magnetar might also undergo subtle changes. The rigid crust, having survived countless quakes, may have been altered by its ordeals, perhaps cracked and reformed enough times to ease the stress points. The internal superfluid may have calmed, and the star's rotation will be extremely steady now, having shed most of its rotational energy. If we could watch a magnetar over a million-year span, we would likely see it drift from the magnetar category into the realm of ordinary neutron stars. Its wild youth of gamma-ray tantrums and X-ray flares would be ancient history. Importantly, even in its quiet retirement, the Magnetar's legacy lives on in various ways. The energy it released in its active period may have left a lasting imprint on its surroundings. Perhaps the interstellar medium around it is slightly enriched or ionized from those early flares. The Magnetar's magnetic field, though decayed, may still influence any nearby plasma or cosmic rays passing by. And from a scientific perspective, the mere fact that we can identify a once magnetar by its residual properties, like a relatively high surface temperature or a still strong field, helps us piece together its life story. Every old neutron star with an unusually high field or an odd quirk might be a former magnetar in disguise. Thus, the life cycle of a magnetar comes full circle. Born in the violence of a supernova, roaring through a brief adolescence of high-energy outbursts, and then gradually calming down over millennia, it converges with the population of standard neutron stars. The transitions it undergoes, from bursting magnetar to high B pulsar to perhaps an inert, cooling core, are a natural progression written by the slow diminishment of its magnetic might. This long goodbye does not carry the drama of the magnetar's earlier chapters. Instead, it is a coda of soft X-ray light and steady spin down, the afterglow of a magnetic tempest. Studying magnetars at every stage, from their formation to their quiet old age, gives astronomers a more complete understanding of neutron star evolution. We can see, in magnetars, how extreme physics changes over time, how ultra-strong fields weaken, how intense activity subsides, and how one exotic class of objects gradually transforms into another. In the universe, even the most furious phenomena eventually ebb. The magnetar's long, quiet tail is a gentle reminder of this cosmic truth. After the fire and fury, what remains is tranquility and the faint memory of former power, encoded in a slowly fading magnetic field and a cooling star that once blazed so brightly. The space around a magnetar becomes an arena of extraordinary upheavals. A calm cosmic vacuum is suddenly electrified by the magnetar's presence. When its magnetic field twists or snaps, it drives shock waves through surrounding gas and dust. In mere instants, an eruption can unleash more energy than the sun emits in 100 millennia. These shock fronts race outward, heating everything in their path. Particles caught in the blast are accelerated to fantastic speeds, and the interstellar gas itself starts to glow from the sudden jolt of heat. Each magnetar flare is like a stone cast into the cosmic pond, sending out ripples of hot, energized matter that can light up the dark around it. It's not only light and heat that magnetars fling into space, but also matter, sometimes in exotic forms. In a colossal flare, the magnetar's crust can fracture, tossing out streams of atomic nuclei. Astronomers now think these eruptions may forge rare heavy elements, gold, platinum, uranium, in the blink of an eye. A single magnetar blast can manufacture and eject as much as 1/10 of the galaxy's supply of such precious metals. The evidence comes from an event so bright that its gamma rays had to be measured as a reflection off our moon. In the debris of that flare, scientists found telltale radioactive afterglows that matched the creation of new elements. Those newborn atoms, hurled into space, will drift and mix into new star systems. One day, they could become part of planets, even part of life itself. In this way, a magnetar's fury seeds the cosmos with fresh matter, a chemical alchemy born of violence. The magnetar's magnetic field doesn't stop at sculpting atoms. it can unmake them too. Near the star, magnetism utterly overwhelms normal matter. If one were unfortunate enough to stray within 1,000 kilometers of a magnetar, the effects would be instantly lethal. The magnetic force would tug the very atoms of your body into thread-like shapes, tearing electrons off their nuclei and turning you into a cloud of charged single atoms. Complex molecules and chemistry cannot survive in such an environment. In essence, a magnetar near miss reduces matter to its most elementary state. Even from far away, the influence can be felt. In December 2004, a magnetar on the other side of the galaxy let loose a flare so intense that it briefly rattled Earth's magnetic field from 50,000 light-years away. Our atmosphere sensed a disturbance, as if a far-off thunder had echoed through space. These extremes show how magnetism meets matter around a magnetar. By shattering atoms up close, heating gases afar, and even stirring detectable changes across astronomical distances. Yet amid this chaos, magnetars also produce fleeting, mysterious signals that have only recently come to light. In April 2020, a split-second burst of radio waves, a fast radio burst, or FRB, was detected within our own galaxy and traced directly to a known magnetar. For years, FRBs had been enigmatic flashes usually seen in distant galaxies. Here, for the first time, one was caught in the act, right next door in cosmic terms. The magnetar had emitted an intense radio pulse alongside a brief X-ray flare. It was as if the magnetar shouted across space in radio waves while convulsing in high-energy light. This event electrified astronomers. It confirmed that magnetars, with their volatile magnetic engines, are a source of these cosmic, millisecond radio blips. The leading idea is that a sudden reconfiguration of the magnetar's field, perhaps a magnetic quake or a shock in its magnetosphere, launched a blast of radio energy outward. In fact, theorists have shown that if a magnetar's crust cracks, it can send a wave through the magnetosphere that steepens into a monster shock, accelerating particles to relativistic speeds. Those particles would then radiate a bright, brief burst of radio waves. In calmer moments, this process would be invisible, but when the magnetar flares, we witness these fast radio bursts as whispers of the dramatic magnetic fireworks happening light-years away. All around a magnetar, the invisible magnetic field is doing visible work. It pumps energy into the environment, heating gas and triggering chemical reactions in space. It can create new atoms through nuclear reactions and destroy molecular bonds through sheer force. It can send out shockwaves that accelerate cosmic particles and radio pulses that briefly outshine entire galaxies. The volume of space influenced by a magnetar's outbursts may span many light-years, a bubble of turbulent, enriched, and ionized material. In a very real sense, magnetars profoundly change the space around them, sculpting nebulae, stirring up the interstellar medium, and contributing freshly made elements to the galactic ecosystem. We see magnetism meeting matter here at its most extreme, a star's magnetic fury imprinted on the cosmos around it, leaving glowing shock fronts, altered atoms, and ghostly bursts of energy that traverse the universe. From the tumult around magnetars, we turn to something quieter, the tenuous rings of matter that sometimes linger in their shadow. After a massive star's final explosion, not everything is always blown away into space. Some remnants of that star can fall back, circling the newborn neutron star like a haunted halo. In a few special cases, astronomers have found hints of fallback disks around magnetars. These are thin disks of debris, ash from the supernova, orbiting the magnetar at a safe distance. They don't shine brightly like the hot accretion disks of black holes. Instead, they glow faintly in infrared light, illuminated by the magnetar's residual heat. One magnetar in particular, known as 4U 0142 plus 61 provided the first compelling evidence of such a disk. Observations with NASA's Spitzer Space Telescope revealed an infrared excess around this magnetar, best explained by a dusty disk of material about 1.6 million kilometers out from the star. The disk carries roughly 10 times the mass of Earth in heavier elements, the burnt leftovers of the star that died 100,000 years ago. It was the first time a neutron star was seen with a substantial debris ring encircling it. This discovery hints that the formation of planets around neutron stars, while exotic, might not be impossible. After all, if a disk of metal-rich dust persists, over millennia it could clump and coagulate into asteroids or even second-generation planets. Within these quiet disks lies a story of cosmic rebirth. The material is not the cool, primordial stuff of normal planet formation, but the processed guts of a star, rich in iron and other heavy elements. As it orbits the magnetar, the disk is likely cold and thin, perhaps studded with crystals of silicate and frozen metal. The magnetar's intense magnetic field may stir the disk at times, but generally this debris is passive, neither raining down onto the star nor being blown away. It's a relic, a leftover ring, much like Saturn's rings, writ large and in strange materials. Over time, this disk can evolve. Grains collide and merge. Some fall inward, some migrate outward. In a few million years, one could imagine chunks coalescing, the birth of rocky bodies born from supernova ashes. Indeed, the first exoplanets ever discovered were around a pulsar, another type of neutron star. Proof that planets can form in the aftermath of stellar death. A fallback disk around a magnetar might similarly be the cradle for such exotic worlds. The idea that a magnetar, a place of such violence, could eventually host a small orbiting planet is a testament to nature's resilience. Even in the corpse of a star, new structures can emerge. These disks don't just offer a potential for planets, they also affect the magnetar itself in subtle ways. A magnetar's rotation might be influenced by a disk's presence. Normally, isolated neutron stars gradually slow their spin over thousands of years due to magnetic braking. They fling out energy and angular momentum via their magnetic fields. But if a magnetar is encircled by a disk of material, that disk can interact with the star's magnetosphere. It might exert a gentle drag, or even, under certain conditions, feed some angular momentum back to the star. Theoretical models suggest that a thin fallback disk could apply a torque that alters the star's spin-down behavior. One enigmatic magnetar, named SGR 0418 plus 5729, provides a tantalizing example. This magnetar puzzled scientists by having an extremely low observed spin-down rate, implying a surface magnetic field far weaker than typical magnetars. In fact, its inferred external field was more akin to a normal pulsar's, around 10 neo-12 Gauss, even though it behaved like a magnetar with bursts and X-ray activity. How could that be? A likely explanation is that SGR 0418's dipole field is partially concealed or effectively reduced, possibly by a fallback disk interacting with it. The disk's presence could twist the magnetic field lines or adjust the braking torque, allowing the magnetar to spin almost without slowing for a long time. In this scenario, the magnetar might still possess a super strong internal magnetic field, driving its bursts, while the disk modulates what we observe externally. This idea, if correct, means that some magnetars might masquerade as weaker, low-field neutron stars at first glance. The fallback material could bury the magnetic field or siphon away rotational energy, leading to atypical spin behavior. Indeed, SGR 0418 went for years without a detected spin period change, until at last a tiny slowdown was measured, confirming its field was surprisingly low on the outside. Such magnetars are a reminder that the story of a neutron star isn't finished when the supernova fades. The environment it finds itself in, whether it's alone, in a binary, or surrounded by a disk, can shape its evolution. Two magnetars may be born with similar magnetic fury, yet one that retains a full-back disk might evolve very differently from one that doesn't. The disk could act as a brake or even a spin regulator, tapping the star's rotation to heat the disk, or causing the star to maintain a steady period longer than it otherwise would. This interplay might explain why magnetars exhibit a range of observed magnetic field strengths and spin rates. They do not all follow one simple path. Some wear a cloak of leftover matter that changes their fate. Encircling disks also raise the fascinating possibility of second-generation planetary systems around magnetars. As extreme as it sounds, if debris can settle into a stable orbit and cool, the basic physics of accretion and coagulation should proceed. Already, astronomers speak of pulsar planets. Planets found orbiting the pulsar B1257+12, formed from a disk of material after its supernova. By analogy, a magnetar's disk, rich in heavy elements, could form metallic asteroids or dwarf planets over long timescales. The magnetar 4U and a few others with infrared excess might be doing this quietly over eons. In a sense, this is nature's way of recycling. The cataclysmic death of a massive star leads to one of the most extreme objects in existence, a magnetar. But around that magnetar, the gentle assembling of dust into rocks and perhaps worlds could represent a kind of rebirth. From supernova chaos to the calm of a nascent planetary system, the cycle continues. It's a striking contrast. A magnetar's lethal magnetism at the core, and perhaps a placid ring of dust and rocks at a remove, quietly orbiting. In the grand scale of time, one can imagine that when the magnetar's fireworks subside after tens of thousands of years, any planets that do form might persist, orbiting a cooling, quiet neutron star cinder. Some of the most intriguing clues to a magnetar's nature come not from the light it emits, but from the way that light is polarized. When light waves travel through or near a magnetar's intense magnetic field, strange things happen. Empty space itself behaves like a prism. In normal conditions, a vacuum is just empty. It has no effect on light. But quantum theory predicts that in an immensely strong magnetic field, even a vacuum becomes birefringent, splitting and polarizing light in a manner analogous to how a crystal might. For decades, this was a purely theoretical prediction, elusive to test in laboratories on Earth. Magnetars, and their high-field neutron star cousins, provided the perfect cosmic laboratory. Recently, astronomers succeeded in detecting signs of this quantum effect. By aiming a powerful telescope at a faint, isolated neutron star, they measured the polarization of its visible light and found it to be aligned in a very specific, unexpected way. About 16% of the star's dim optical glow was linearly polarized, far more than could be explained by ordinary processes. The best explanation was exactly the vacuum birefringence idea. The space around the neutron star, threaded by a magnetic field billions of times stronger than Earth's, was birefringent and was forcing the light into a certain polarization state. In essence, the magnetar's field imprinted a signature on the light, whispering of quantum effects in action. This was the first observational hint that the vacuum of space, in the presence of an extreme magnetic field, does not behave like an ordinary void. Magnetars also allow us to test these effects at even higher energies. In 2022, a new space telescope, the Imaging X-ray Polarimetry Explorer, IXPE, turned its eyes to the magnetar 4U, the same one known to have a dust disk. IXPE measures the polarization of X-rays, which are emitted from the hot surface and magnetosphere of the magnetar. The results were astonishing. They found that the X-ray light's polarization behavior changed dramatically with energy. At lower X-ray energies, around 2 to 4 keV, the radiation was polarized in one direction, but at higher energies, above 5 keV, it was polarized at a right angle to the first. In fact, through the middle of IXPE's energy range, the polarization angle swung by 90 degrees, flipping its orientation as the photon energy increased. At the same time, the degree of polarization rose, reaching over 40% at the highest X-ray energies observed. This kind of polarization, tune shift, is exactly what theorists anticipated if magnetar X-rays pass through a region of mixed plasma and vacuum polarization effects. Essentially, the magnetar's magnetized atmosphere creates two modes for light, ordinary and extraordinary polarization modes, and as photons travel outward, one mode can convert into the other at a specific energy, the so-called vacuum resonance. The 90-degree flip in polarization angle corresponds to that resonance point, where the light switches its preferred polarization mode. This is a direct probe of quantum electrodynamics in the harshest regime. It tells us that the magnetar's magnetic field is indeed high enough, around 10^14 Gauss, to induce these effects, and that the magnetar likely has a thin atmosphere of partially ionized heavy elements that lets this mode conversion happen. Polarimetry, the study of light's orientation, has thus opened a new window onto magnetars. It not only confirms exotic physics, like vacuum birefringence, but also gives clues about the magnetar itself. The same IXPE observations suggested that the surface of 4U might be something very exotic, possibly a solid crust with no normal atmosphere at all. The data fit a scenario where the magnetar's surface is in a crystalline state, an ultra-dense solid rather than a gaseous atmosphere. In such a case, the X-rays we see come directly from a hot, solid neutron star surface and from its magnetosphere, without a fog of gas to depolarize them. This intriguing result is consistent with the idea of a neutron star's outer layers freezing into a solid due to immense magnetic pressure. It's a glimpse into the magnetar's very skin. Additionally, polarization measurements allow astronomers to infer the geometry of the magnetic field, whether it's a tidy dipole or distorted by twists. As the magnetar rotates, any wobble or asymmetry in polarization can reveal the alignment of its magnetic and spin axes. These techniques are in early days, but as we collect more polarized light from magnetars, we'll be mapping their magnetic topography and testing our understanding of quantum physics under extreme conditions. The sky around magnetars can also shine in polarized optical light, as was seen with that isolated neutron star RX J1956. Though not a magnetar by strength, it taught us what to look for: a significant polarized signal that couldn't be explained without invoking magnetism's quantum influence. In magnetars, any optical or infrared light, perhaps from their dust disks, might carry similar imprints. Each photon becomes a storyteller, encoding the conditions it experienced near the magnetar. When we measure that polarization, whether in optical wavelengths from a cooler neutron star or in X-rays from a hot magnetar, we are effectively performing a remote experiment in physics. We confirm that a vacuum isn't truly empty when a magnetar is present. It's filled with virtual particles that dance in the magnetic field and alter how light moves. This knowledge strengthens our confidence in QED, quantum electrodynamics, an 80-year-old prediction finally observed. It's poetic that such fundamental physics is tested not in a lab on Earth, but by observing a tiny, dead star nearly 400 light-years away. Magnetars, with their polarized skies, thus bridge the very large astrophysical observations and the very small quantum behavior of vacuums. They remind us that the universe often provides its own natural laboratories for the curious mind. Amid the intermittent fury of magnetars, there is a bedrock of regularity. These objects rotate, and with each rotation they send us pulses of radiation. But unlike the well-behaved ticking of some pulsars, magnetars reveal their turbulent nature in the irregularities of their rotation. Keep a magnetar under close watch, and you will notice that its spins are not perfectly uniform. They exhibit timing noise, minute wanderings in the rotational period that hint at unsteady processes within. More dramatically, magnetars, like many neutron stars, can undergo sudden jolts known as glitches. A glitch is a moment when the star's rotation abruptly speeds up, as if the magnetar hiccuped and spun a little faster. For ordinary pulsars, glitches are attributed to superfluid layers inside the star transferring angular momentum to the crust, essentially the inside briefly outpacing the outside. In the hundreds of glitches observed across pulsars and magnetars, this has almost always been seen as a spin-up. The magnetar's crust, stressed and slowed by magnetic braking, suddenly gets a push from the faster rotating superfluid core, and the whole star's spin jumps slightly. It's like a spring under tension that slips a notch. The magnetar then gradually settles, slowing down steadily again until perhaps months or years later, another glitch strikes. These events tell us that a neutron star's interior is not a rigid sphere, but a complex layered system with differential rotation and pent-up energy. Magnetars, however, have added new twists to this story of glitches. In one remarkable case, a magnetar did something nearly unheard of. It slowed down abruptly. This was the magnetar 1E 22259 plus 586, which in 2002 surprised observers with a brief X-ray outburst. Upon examining its rotation, astronomers discovered a strange anomaly, an anti-glitch. Instead of speeding up, the star's spin frequency dropped suddenly, as if the crust was braked hard for a moment. This backwards glitch was accompanied by multiple X-ray bursts and a change in the long-term spin-down rate of the star. Such behavior was not predicted by any standard model of neutron star rotation. It challenged our understanding, suggesting that magnetar crusts might sometimes decouple and lose angular momentum catastrophically, perhaps due to a massive internal magnetic reconfiguration, or a brief coupling to something like a stellar wind. If the cause is internal, it points to differential rotation. Maybe the crust briefly lagged behind the core, rather than catching up to it. The anti-glitch forced theorists to rethink glitch physics, considering that a magnetar's intense magnetic stresses might lead to outcomes not seen in tamer pulsars. For example, a sudden energy release could create a wind of charged particles that puts a brake on the crust, or magnetic tension could jerk the crust in the opposite direction of rotation. This event remains one of the few of its kind, marking magnetars as even more capricious timekeepers. Even the more ordinary glitches in magnetars tend to be entwined with their magnetic personalities. Often, a magnetar glitch is accompanied by changes in X-ray emission, or even the onset of a short bursting episode. It's as if the starquake that causes the glitch also fractures magnetic field lines, leading to particle acceleration and X-ray outbursts. In one instance, a magnetar exhibited a glitch contemporaneous with a flurry of soft gamma-ray bursts. Such linkage between timing and high-energy output highlights that for magnetars, rotation and magnetism are deeply interwoven. The crust's motion can liberate magnetic energy, and conversely, the magnetic field's evolution can influence rotation, The precise timing of magnetar rotations also enables us to probe their interiors. After some glitches, magnetars show a recovery, where the spin gradually relaxes back toward its pre-glitch rate, possibly revealing the viscosity of superfluid components or the repinning of vortices inside the star. These recoveries give clues about the ultra-dense matter within, something we cannot replicate on Earth. The incredible precision of modern observational tools means we can measure a magnetar's spin period down to millionths of a second. By doing so over years, we uncover a kind of heartbeat of the star. And in magnetars, that heartbeat sometimes stutters. This timing noise, tiny irregular fluctuations superposed on the steady slowdown, might be due to small-scale magnetic irregularities, like the crust crinkling slowly, or continual interactions between the crust and core. It's analogous to listening to a mighty engine and hearing faint knocks and pings that betray its inner workings. In magnetars, the timing noise is generally larger than in run-of-the-mill pulsars, which hints that their magnetospheric torque, the braking force of the magnetic wind, might be fluctuating. The magnetar's twisting, untwisting field could modulate the wind and hence the spin down, leading to a noisy slowdown.
A recent development in this realm of timing is particularly fascinating. A connection between magnetar timing irregularities and fast radio bursts. In 2020, the Galactic magnetar SGR 1935+2-154 emitted the first known FRB from within the Milky Way. Follow-up studies indicated that around the time of some bursts, the magnetar's rotation may have changed in subtle ways. And just this year, another magnetar associated with recurrent FRBs showed hints of rapid spin changes coincident with its radio bursts. If confirmed, this means that when the magnetar undergoes one of these mysterious radio outbursts, it might actually be experiencing a disturbance strong enough to alter its rotation slightly.
It's a profound hint that FRBs, at least those from magnetars, are linked to internal seismic or magnetic events of great significance, enough to affect the star's rotation. Imagine the magnetar's crust cracking or magnetosphere erupting. Not only does it send a radio flash across the universe, but it momentarily jerks the star's spin. This is a frontier of current research, with scientists closely monitoring magnetar spin evolution during and after bursts to catch such connections. It underscores that in magnetars, every aspect of behavior, high energy emission, low energy radio flashes, rotation, are pieces of one grand puzzle. By tracking the ticks of these stellar clocks and noticing when a tick comes early or late, we are effectively feeling the tremors of the star's crust and magnetic core. The timing studies of magnetars have already expanded our understanding of neutron star interiors. The anti-glitch of 1E 2259+586, for example, strongly hints at differential rotation and previously unknown coupling mechanisms inside the star. It may be that the core and crust can momentarily slip against each other in ways we hadn't appreciated, mediated by the fluid's vortices and magnetic flux tubes. Each glitch and anti-glitch provides data points to refine models of neutron star matter. How a superfluid rotates, how a solid crust yields under stress, and how magnetism ties it all together. In the broader context, magnetar timing irregularities prepare us for the unexpected. They remind us that even something as stable as a spinning neutron star can surprise us with a sudden lurch. Precision monitoring of these cosmic clocks thus serves as both a diagnostic tool for fundamental physics and a lesson in humility. The universe's most reliable clocks still have secrets up their sleeves. While magnetars announce themselves through light and electromagnetic fury, they may also stir the fabric of spacetime and produce more ghostly messengers. Scientists have long wondered if the convulsions of a magnetar, its quakes and flares, generate gravitational waves or bursts of neutrinos. These would be faint and hard to catch, but the prospects are tantalizing because they would carry information directly from within the star's core. During a magnetar's giant flare, the internal neutron star might ring like a bell, setting off oscillations that emit gravitational waves, ripples in spacetime itself. Some models predict that when a magnetar's magnetic field rearranges catastrophically, the crust and core could deform and vibrate, exciting modes like the fabled F mode, a fundamental oscillation of the star that radiate gravitational energy. Similarly, the quasi-periodic oscillations observed in the X-ray tail of giant flares might correspond to mechanical vibrations of the crust. If so, those mechanical vibrations could couple to gravitational waves as well. Modern gravitational wave observatories, like LIGO and Virgo, have actually conducted searches for these signals. In one search, scientists looked at data around the times of known magnetar bursts, including a few short bursts and the rare giant flare candidates, to see if any coincident gravitational wave chirps appeared. So far, the result has been silence. No definitive detection of gravitational waves from a magnetar event. But this silence is itself instructive. From it, researchers can place an upper limit on how much energy in gravitational waves those magnetar flares could have emitted. The limits suggest that only a tiny fraction of the flare's colossal energy went into shaking spacetime. The bulk was in photons and particle kinetic energy. However, as gravitational wave detectors become more sensitive, the next giant flare in our local group of galaxies might be the one to tip the scales. Even a non-detection refines our models. For instance, if a magnetar's core oscillations damp out too quickly, or if they are axisymmetric, they might produce weaker gravitational waves. So the quest continues, with each magnetar burst being a potential natural experiment. The realm of neutrinos offers another angle. Neutrinos are nearly massless, elusive particles that are produced in copious amounts when nuclear reactions or extreme particle interactions occur. A newly born magnetar from a supernova certainly emits a flood of neutrinos, as every newborn neutron star does, carrying away the energy of the collapsing core. Those neutrinos famously were detected from supernova 1987A, likely signaling the birth of a neutron star, or magnetar, in the Large Magellanic Cloud. But what about later in a magnetar's life? Theories suggest that magnetar flares, especially the giant ones, could involve hadronic processes, that is, atomic nuclei being accelerated to high energies and colliding. In such violent collisions, pions and other particles can be created, which then decay into high-energy neutrinos. If magnetar-driven shocks accelerate protons to cosmic ray energies, those protons might slam into surrounding matter or photon fields to produce neutrinos. Thus, magnetars could be occasional point sources of neutrino flashes. Astronomers have used instruments like the Ice Cube Neutrino Observatory, a vast detector buried in Antarctic ice, to hunt for neutrinos arriving from the directions of known magnetars. Over 14 years of data, they have searched for statistically significant clusters of neutrino events in time and space, coincident with magnetar bursts. So far, these searches haven't found a clear neutrino signal that can be attributed to magnetars. This null result again sets limits. If magnetars produce neutrinos, it's below Ice Cube's current sensitivity, or such events are very rare. Still, the possibility remains intriguing. Magnetars might be one contributor to the sea of cosmic rays and neutrinos that fill our galaxy. In fact, the study that identified magnetars as heavy element factories also speculated that magnetar flares could be a source of heavy cosmic rays, meaning extremely fast nuclei like iron or gold atoms hurtling through space. If magnetars can accelerate such massive particles, some of those interactions would inevitably produce neutrinos as byproducts, Each magnetar giant flare could thus be a mini cosmic ray accelerator, injecting both charged particles and neutrinos into the galactic environment. Detecting neutrinos from a magnetar flare would be like hearing a star's heartbeat via an entirely different sense, a nearly invisible whisper from deep within the event. Neutrinos can escape straight through the dense interior of a neutron star, if conditions allow, bringing news from regions we cannot see with light. For now, we have only upper bounds and theoretical predictions. But future neutrino detectors, or perhaps a lucky nearby magnetar flare, might yield the first neutrino flash from a magnetar. If that day comes, imagine what it would mean. We could watch a magnetar flare in gamma rays and X-rays, listen for its gravitational shudder in LIGO's data, and catch the ethereal neutrinos that fly out from the heart of the event. It would be a multi-messenger portrait of a magnetar's wrath. The neutrinos would announce the hadronic interactions and possibly quark processes in the magnetar's core or magnetosphere, while gravitational waves would sketch the mechanical deformation of the star, and electromagnetic signals would show the aftermath in the magnetosphere and environment. We got a taste of multi-messenger insight with the neutron-star merger of 2017, gravitational waves and light together. A magnetar flare could be the next big step, bringing neutrinos into the fold. And even without a detection yet, the ongoing searches themselves push our understanding. They make us quantify how much energy is or isn't going into these channels, tightening the constraints on magnetar flare models. Magnetars in this way sit at a crossroad of different messengers. Their light tells of surface and magnetospheric chaos. Their timing hints at interior dynamics. Potential gravitational waves would reveal core oscillations. Potential neutrinos would confirm high-energy particle accelerators at work. Each messenger complements the others. It is a sober thought that a magnetar, an object only some tens of kilometers across, can create disturbances that propagate in fundamentally different ways, as undulations of spacetime and as nearly undetectable neutrinos flying through the cosmos. The lack of observed ripples, or neutrinos, so far simply underscores how extreme and rare the conditions must be to produce them in abundance. Giant flares themselves are thought to occur perhaps a few times per century, per galaxy at most. We were fortunate to catch one in 2004 and its impact on Earth's ionosphere, and one just beyond our galaxy in 2020. The next could happen tomorrow or in 50 years. When it does, a global network of detectors will be waiting, eager to capture every facet of the event. Through these efforts, magnetars continue to be focal points of discovery, teaching us not just about their own nature, but also testing the fundamental laws of physics under extreme conditions. As we delve into what magnetars hurl into space, another question arises. What do magnetars themselves contribute to the cosmic environment over the long term? One answer seems to lie in cosmic rays. Cosmic rays are high-speed atomic particles, mostly protons and heavier nuclei, that zip through the galaxy, occasionally pinging our atmosphere and creating showers of secondary particles. They are part of the galactic weather, influencing everything from cloud ionization to the chemistry of interstellar clouds. Traditionally, supernova shockwaves have been considered the primary accelerators of cosmic rays in our galaxy. But magnetars, with their combination of supernova origins and extreme fields, are now thought to play a niche but significant role. When a magnetar flares, the shockwave it sends out can accelerate charged particles, much like a supernova remnant does, but on a shorter timescale. In fact, the 2020 flare from a magnetar in galaxy NGC 253, 11 million light-years away, was so energetic that had such an event occurred in our own galaxy, it could have showered nearby space with high-energy particles equivalent to what a supernova releases. Researchers have theorized that magnetar flares might specifically produce heavy cosmic ray nuclei. These would be atoms like iron or even heavier elements, energized to nearly light speed. Since magnetar flares create heavy elements to begin with, it makes sense that some fraction of those freshly minted atoms could be hurled out as cosmic rays. The notion is that up to 10% of the Milky Way's heavy elements might come from magnetar ejecta, and along with those ejecta, heavy nuclei cosmic rays would be injected into the galaxy's pool of high-energy particles. If magnetars are cosmic ray factories, they add a wildcard element to the galaxy's ecosystem. Most cosmic rays are protons from supernovae, but a magnetar's contribution might skew toward heavier species and possibly higher energies for short bursts. Once launched, these particles roam the galaxy, their paths bent by magnetic fields, eventually perhaps reaching places like Earth. It's conceivable that a small fraction of the rare iron nuclei we see in cosmic ray detectors were accelerated in a single magnetar outburst thousands of years ago. In doing so, magnetars contribute to the ongoing process of ionization and heating of the interstellar medium, a key aspect of what one might call galactic weather. Cosmic rays ionize dense molecular clouds, affecting chemistry and potentially the collapse of those clouds into new stars. They also deposit energy throughout the galaxy, providing pressure that counteracts gravity in galactic disks. Magnetars, though few, could disproportionately influence this by injecting very energetic particles during their brief active phases. Another mechanism for cosmic ray production in magnetars could be through their steady winds. Magnetars are known to sometimes have a particle wind flowing out from their magnetospheres. Especially during active periods, a magnetar might drive a relativistic wind of electrons and positrons, and maybe heavier ions, outwards. As this wind slams into the surrounding medium, it forms a bow shock if the magnetar is moving, or a shock front that can also accelerate particles. There's evidence that at least one magnetar has a surrounding nebula, a cloud of high-energy particles and shocked gas, somewhat analogous to the Crab Nebula, which is powered by a pulsar wind. In the case of magnetars, such nebulae would be energized by magnetic field decay, powering the outflow. The shock at the interface of the magnetar wind and the interstellar medium can act as an acceleration site, boosting particles to high energies via the well-known Fermi acceleration process. Thus, even in their quiescence, magnetars may be seeding their neighborhoods with cosmic rays gradually. These contributions, while not dominant compared to all supernova remnants, add diversity to the energy distribution of cosmic rays. They might, for example, be a source of extremely high-energy electrons or positrons that have been hinted at by observations, such as excess high-energy positrons near Earth. When we speak of galactic weather, we evoke the idea that the galaxy has a climate influenced by stars and stellar remnants. Magnetars are like sudden storms in that climate, brief, intense events that can redistribute energy and matter. After a magnetar flare, the local region, perhaps dozens of light years across, is bathed in radiation and energetic particles. Gas clouds in that vicinity might experience rapid chemical changes. Complex molecules could be broken apart by radiation, ices on dust grains could sublimate, and new reaction pathways could open in the ionized gas. Over centuries, as the shockwave travels outwards, it compresses some areas and rarefies others. It might trigger star formation in a nearby cloud by compression, or conversely, it might evaporate a fragile small clump of gas, preventing a star from forming. In these ways, magnetars integrate into the tapestry of stellar feedback processes. They are a part of how galaxies recycle material and regulate star birth. They sit alongside supernovae and stellar winds as agents of change. The key difference is that magnetar contributions are more impulsive and rare. A given star-forming region might see a steady drizzle of ultraviolet from massive stars and occasional supernova shock, but a magnetar flare would be like a lightning strike, unanticipated and forceful. It could, in principle, account for some unique isotopic signatures in cosmic ray composition, or create expanding bubbles of hot gas that later show up as X-ray shells. The heavy elements flung out by magnetars also eventually become part of cosmic dust and cosmic rays. For instance, when a magnetar flare produces gold or platinum atoms and sends them out, those atoms might travel and later condense onto dust grains in cooler regions. Some of those grains could find their way into new solar systems, meaning that a planet somewhere might have a share of atoms forged in a magnetar event. It's a profound thought. Our jewelry's gold, as one example, might partly owe to not just kilonovae, neutron star mergers, but possibly magnetar tantrums. And if those atoms were accelerated as cosmic rays, they might have traversed the galaxy, only to be stopped when they collided with a cloud or an atmosphere, contributing to cosmic ray spallation processes that create some of the rare elements like lithium and beryllium. Thus, magnetars tie into the cosmic chemical cycle in multiple ways, as creators of elements and as accelerators of nuclei. In summary, magnetars, through their crustal jolts and shock waves, likely play a supporting role in populating the Milky Way with cosmic rays and shaping the state of the interstellar medium. They are not the sole sculptors of galactic weather, but they are unique ones. They preferentially contribute the highest energy bursts of particles and some of the heaviest species of cosmic rays. Each magnetar flare is a point injection of energy that diffuses through the galaxy over eons. Our detectors have started to pick up these clues. The theorized heavy cosmic rays from magnetars remain a topic of investigation, and future instruments may detect telltale signatures, like unusual energy spectra or anisotropies, that trace back to past magnetar events. The galactic environment we live in, bathed in a low-level haze of radiation and high-speed particles, has contributions from countless sources. Magnetars are among the most dramatic of those, proving yet again that these extreme stars leave marks far beyond their immediate vicinity. Magnetars are extraordinary, but a natural question arises. Why are they so rare? Out of the many neutron stars born from supernovae, only a small fraction manifest these ultra-strong magnetic fields and exotic behaviors. By current estimates, perhaps 1 in 10 neutron stars becomes a magnetar. In our galaxy, we know of roughly 30 confirmed magnetars versus around 3,000 ordinary pulsars. This selectiveness hints that special conditions at birth are required. To unlock this mystery, astronomers and theorists look at the lives of massive stars, the progenitors, and the physics of core collapse. It appears that 2 main ingredients strongly influence magnetar birth: the star's rotation rate and its metallicity, metal content. The leading theory is the fast dynamo scenario. If a collapsing stellar core is rotating exceptionally fast, on the order of a few milliseconds per rotation, it can amplify magnetic fields to magnetar strength during the brief proto-neutron star phase. Essentially, the newborn neutron star's convection and rotation set up a powerful dynamo, similar in concept to how Earth's spinning iron core generates its magnetic field, but vastly more intense. This convective dynamo can take the tiny magnetic seed fields and boost them to 10^15 Gauss in a matter of seconds. The catch is that to achieve this, the rotation must be very rapid, a Rossby number below a certain threshold, where rotation dominates convection. That typically means the stellar core, at the moment of collapse, was spinning extremely quickly, likely due to a combination of the star's initial spin and any spin-up during collapse. If this happens, the outcome is a magnetar, a highly magnetized, initially rapidly spinning neutron star that then quickly slows as its huge magnetic field breaks it. If the rotation is only moderate, the dynamo doesn't kick in strongly, and a more typical 10-12, 10-13 Gauss pulsar emerges. This naturally explains the dichotomy we see. Magnetars have ultra-strong fields and tend to have longer spin periods, seconds, whereas young pulsars have weaker fields and can spin faster, tens of milliseconds. The theory goes that the magnetar's initial rapid spin was immediately checked by its own potent magnetic winds, leaving it rotating relatively slowly, a few seconds period, even when quite young. Meanwhile, a neutron star born with a weaker field doesn't break as hard, so if it started with a moderate rotation, it remains fairly fast spinning as a young pulsar. Why would only 10% of neutron stars get that fast spin at birth? This is where metallicity and progenitor characteristics come into play. High metallicity massive stars, those with lots of heavy elements, tend to drive strong stellar winds in their late stages. These winds carry away angular momentum. In contrast, lower metallicity stars have weaker winds, so they can retain more of their spin-up to collapse. Studies of superluminous supernovae and long gamma-ray bursts, which are extreme explosions likely powered by millisecond magnetars or black hole engines, show a preference for low metallicity environments, typically about half solar metallicity or less. This lines up with the idea that to produce a magnetar, especially an ultra-fast spinning one that might power a superluminous SN, it helps if the star didn't lose its rotational energy to winds. Additionally, binary interactions can play a role. A star in a close binary might be spun up by mass transfer, a process akin to pushing a playground merry-go-round, ending its life rotating faster than it formed. Such a scenario could also yield a magnetar. There's evidence that many magnetars might come from more massive stars than typical pulsars, suggesting perhaps initial mass above some threshold, and possibly binary evolution pathways. For instance, some magnetars are associated with clusters of very massive stars, the so-called magnetar birth clusters, hinting they came from stars perhaps 30-40 solar masses that underwent heavy mass loss, perhaps aided by binary stripping, leaving behind a fast-spinning core. In simple terms, to get a magnetar, nature likely needs to cook the neutron star core in just the right way, spin it swiftly, and maybe inject some turbulence. The spin is like the egg beater that stirs the magnetic fields. Metallicity is like the viscosity of the batter. Low metallicity means the batter, star, stays mixed and doesn't slow down too much. When the star explodes, the combination yields a field amplification. If any one factor is off, if the star was too slow, or if it shed too much spin via winds, or if it lacked convection oomph, then the dynamo might produce a normal field instead. The Taylor-Spruitt dynamo, a specific variant, has even been proposed for relatively slower rotating cores that are spun up by fallback accretion. This could account for magnetars that aren't born with ultra-fast spins, periods 10-20 ems rather than 1-5 ems. In those cases, a brief post-supernova fallback of material might impart angular momentum to the proto-neutron star, enough to drive a different kind of dynamo and generate a strong field. Such magnetars might start with somewhat lower field or be low-field magnetars, whose dipole is power 10 or 13 G, and indeed we see a subclass of magnetars with fields in that range, but still magnetar-like X-ray bursts. It suggests multiple channels, a high spin channel for classical magnetars, and a moderate spin plus fallback channel for low-field magnetars. In either case, something extra at birth sets these objects apart. Observationally, Magnetars have been connected to some unusual stellar explosions. A few superluminous supernovae, SLSNE, those 10 to 100 times brighter than normal, can be fit by models where a newborn magnetar injects energy into the exploding ejector, keeping it hot and luminous for an extended period. These models require a magnetar with a millisecond initial period and field 1014 to 1015 G. The host galaxies of SLSNE often have low metallicity and high specific star formation rates, again aligning with the idea of fast-rotating progenitors. Magnetars have also been speculated to arise more in certain environments. For instance, the galactic center region hosts a magnetar close to the central black hole, possibly hinting that dense stellar environments or dynamical interactions could affect their formation rate. But overall, the magnetar fraction, 10%, suggests that nature's recipe for a magnetar is a bit special, but not exceedingly rare. It could simply be that any massive star that retains enough spin will do the trick. If roughly 10% of core collapses yield that condition, we get 10% magnetars. This fraction might also vary with cosmic time and environment. Perhaps in the earlier universe, with generally lower metallicity, magnetars were more common. And indeed, FRBs, which may be magnetars, have been observed at cosmological distances, implying magnetars are being born in other galaxies at rates consistent with a few to 10% of supernovae. The role of metallicity was dramatically illustrated by gamma-ray bursts. Long-duration GRBs, the death cries of massive stars, favor low metallicity galaxies, because those stars likely needed to be fast spinning to produce the GRB, similar to magnetar formation. Magnetars are thought to be one possible central engine of GRBs, providing the extreme energy via rapid spin down. If a magnetar is born spinning in 1 mems, it has an enormous rotational energy that can be tapped to power a GRB jet. Many GRB models invoke a magnetar that loses its spin energy over tens of seconds, driving a relativistic outflow. So magnetars might be behind some of the most spectacular explosions in the universe. However, if the progenitor's metallicity were higher, it might not have been able to keep that spin, thus failing to produce a magnetar-level field or a GRB. All these clues converge to a picture. Only some stars, under only some conditions, give rise to magnetars. They are the chosen few that were born in a cosmic hurry, spinning like an ice skater pulling in their arms, and possibly nurtured in environments that didn't rob them of that momentum. The consequences of this are evident in the statistics. We have about 30 magnetars known in the Milky Way, and a handful more candidates, compared to thousands of neutron stars that are ordinary. And even among those 30, we see diversity. Some have super strong dipoles, others, low B magnetars, have dipole fields, only an order of magnitude above pulsar values but presumably strong internal fields. This suggests perhaps a continuum, or multiple pathways, to magnetar-like behavior. Indeed, one might ask, could some neutron stars switch on magnetar-like activity later in life, if their interior fields emerge? It's been speculated that even a neutron star born normal could become a magnetar, if, say, its interior magnetic flux was buried and then reasserts itself. The magnetar fraction could thus grow over time if some objects transition. Alternatively, magnetars might evolve out of their extreme phase after a few thousand years, becoming more like ordinary pulsars as their fields decay. We do see older magnetars, the so-called transient magnetars, or those in high-mass X-ray binaries, that have slower spins and lower inferred fields, possibly indicating we catch some magnetars late in life, looking more tame. so part of why only some is also why not forever. Magnetars likely don't remain magnetars for the full billion-year potential life of a neutron star. Their strong fields decay on timescales of 10^4, 10^5 years, after which they might become quiet. This means some fraction of apparently normal neutron stars could be retired magnetars in disguise. In essence, magnetars are a cosmic rarity created by youthful extravagance. A youthful neutron star with extravagant rotation and magnetic amplification. They are born in special stellar furnaces, often massive, possibly low metallicity ones, and live fast, emitting tremendous energy early on. Their distinctness teaches us about the range of possibilities for neutron stars. By studying magnetars, we learn about the limits of magnetic field generation, the influence of environment on stellar evolution, and the ultimate fates of the most massive stars. We also glean that the universe, ever inventive, doesn't make every neutron star the same. Some are endowed with magnetic muscles far beyond the norm, and those few go on to shape their surroundings and captivate our imagination disproportionately to their numbers. Across all these explorations of magnetars, their outbursts, disks, polarization signals, timing quirks, and births, lies a deeper theme. Extremes scale up and echo throughout the cosmos. Magnetars are often described as the most magnetic objects in the universe. Quasars, on the other hand, are among the most luminous and powerful persistent beacons, powered by supermassive black holes in distant galaxies. At first glance, magnetars and quasars seem unrelated. One is a city-sized stellar corpse, the other a galaxy-scale phenomenon. Yet, there is a bridge between them, built of the fundamental forces at play. Both magnetars and quasars are dominated by intense magnetic fields and rotation. In a magnetar, it's the rotation of a neutron star and its internal dynamo generating a magnetic field that dominates its behavior. In a quasar, it's the rotation of a black hole or its accretion disk, threading magnetic fields that powers jets and stupendous radiation output. Essentially, magnetars are to neutron stars what quasars are to black holes, an extreme manifestation of energy extraction and conversion via magnetic fields. Studying magnetars can inform our understanding of quasars because many physical processes are scale invariant. Magnetic reconnection, for instance, the process suspected to trigger magnetar flares when field lines snap and realign, is also thought to occur in the coronae of accretion disks around black holes, flares observed from supermassive black hole systems, like the rapid X-ray flares from the Galactic Center's black hole, SCAR-A, or from active galactic nuclei, could be analogous to magnetar flares, just in a much larger system. The physics of plasma in a strong field, the sudden release of magnetic energy, particle acceleration, and radiation, all these have parallels. A magnetar's magnetosphere is a minuscule bubble compared to a quasar's environment, but both might experience a build-up of magnetic stress leading to explosive reconnection events. By analyzing magnetar flares in detail, we refine models of how magnetic energy is stored and released, models that can be applied to quasar disk flares or jet variability. There's also the link of polarization. Magnetars taught us about vacuum birefringence and polarized X-rays. Interestingly, polarization is a crucial tool in studying quasars and active galactic nuclei, AGN, as well. The light from AGN jets is often highly polarized due to synchrotron emission in ordered magnetic fields. Quasar light that echoes off dust or accretion disk winds carries polarization signatures that reveal the geometry of those regions. Even the recent breathtaking images of the shadow of the M87 black hole included polarimetric data, showing the polarization pattern of light around the black hole, which maps the magnetic fields in the accretion flow. In essence, both magnetars and quasars push the frontier of what polarimetry can do, one in the quantum domain, the other in mapping cosmic-scale magnetic structures. The concept that space can affect light's polarization in magnetars might find an analogue in strong gravity environments. Around black holes, general relativity and magnetized plasma also influence polarization through Faraday rotation and gravitational light bending. The lessons we learn in one regime inform the other. For example, the tools and techniques developed to interpret XP data for magnetars can be adapted to future X-ray polarimetry of AGN coronae. Magnetars also present a microcosm of how rotating objects plus magnetic fields can yield collimated outflows. A magnetar's rotational energy and field drive a wind. In quasars, a rotating black hole and its magnetic field, via the Blandford-Znaiec process, launch relativistic jets. The efficiency of energy extraction in both cases depends on magnetic field configuration and rotation speed. When we see a pulsar wind nebula or a magnetar wind nebula, we catch a glimpse of magnetically driven outflow on a small scale, a mixture of toroidal and poloidal fields shaping a wind termination shock. Quasar jets, enormously larger, behave according to similar magneto-hydrodynamic principles. They likely begin as tightly wound helical magnetic fields that gradually expand and accelerate particles, producing synchrotron light. The theory of how energy flows from rotation to particles has been studied deeply in pulsar wind theory, which in turn has influenced jet theory. In pulsars and magnetars, the concept of a light cylinder, beyond which co-rotation can't be maintained, and a striped wind has analogues in the accretion disk winds and jets of black holes, with the Alfvén surface or magnetospheric radius in disks. Thus, by mastering the physics of magnetar magnetospheres, we improve our understanding of scaled-up magnetospheres around black holes. Even the notion of an accretion disk around a magnetar, the fallback disk, touches on quasar physics. Quasars are essentially black holes with accretion disks. In both cases, you have a compact object plus a disk, and magnetic interactions between them can be crucial. In magnetars, a fallback disk might break the star's spin by magnetic coupling, a scenario akin to disk breaking in some young pulsars. In black hole systems, the disk's magnetic field feeds the Blandford-Znaiec mechanism, effectively linking the disk and hole via magnetic field lines and extracting rotational energy. The magnetar is obviously a different beast, a hard surface and magnetic dipole versus an event horizon. But the coupling of a magnetic object with a disk is a common theme. And remarkably, 4U0142 plus 61's discovery of a disk even raises a speculative analogy. Could some neutron stars with disks power something analogous to mini-quasars? They wouldn't be nearly as powerful, but if material falls in, could the magnetar's field produce jets? There have been hints of transient radio outbursts in a few magnetars that resemble weak, clumsy jets. Perhaps studying those will shed light on the ingredients needed for the more prodigious quasar jets. One literal bridge between magnetars and quasars is the case of a magnetar near a supermassive black hole. In our own galactic center, as mentioned, lies a magnetar, SGR J11745 to 2900, orbiting just a few light hours from Sagittarius A, the central black hole. This magnetar has been used as a probe. By measuring how its radio pulses are slowed and twisted, dispersion and Faraday rotation, passing near the black hole, astronomers glean information about the plasma and magnetic field around the black hole itself. It's a beautiful synergy, a cosmic fortuity, where a magnetar serves as a flashlight shining through the environment of a quasar-like object. Our black hole is not a quasar currently, but in physics, it's the same type of object, albeit underfed. The magnetar's signals carry the imprint of the black hole's magnetized surroundings, allowing scientists to measure things like electron densities and magnetic field strengths near CRA. This is a direct instance of how understanding magnetars and using them as tools can inform our picture of quasar environments. It underscores that the physics from one scale can be applied to another. The dispersive delays and Faraday rotation seen for the magnetar pulses are essentially the same processes that occur in quasar radio jets traveling through intergalactic plasma, just observed in a more controlled local setting. On a more conceptual level, magnetars and quasars both exemplify how magnetic energy can dominate gravity under certain conditions. In a magnetar, despite the immense gravitational force binding everything, the magnetic pressure in the crust and exterior is so high that it fractures the star's crust and powers emission far beyond what the residual heat could do. In quasars, the magnetic fields in the disk and black hole vicinity channel gravitational energy from infalling matter or spin into directed outflows and radiation, creating jets that can push out against the host galaxy's interstellar medium. Both are cases of electromagnetic forces engineering the escape of energy from a compact object. Thus, magnetars are sometimes dubbed electromagnetically powered neutron stars, whereas quasars are accretion magnetically powered black holes. The dominance of magnetism unites them. If we can solve how magnetars work, how exactly the magnetic field evolves, how it accelerates particles, how it triggers flares, we will be better equipped to decode observations of distant quasars flickering and flaring. Conversely, insights from AGN studies, like how magnetic reconnection might drive rapid gamma-ray flares in blazar jets, might inspire new ways to think about magnetar flares. The scales differ by many orders of magnitude, but the equations of magnetohydrodynamics and electrodynamics are the same. In the end, magnetars prepare us for thinking big. They are the most extreme objects on a stellar scale. Quasars are among the most extreme on a galactic scale. By understanding one, we build intuition for the other. The universe often uses similar tricks at different scales, a kind of self-similarity. A spinning object with a magnetic field is a timeless theme, whether that object is 20 kilometers across or 20 million. As we conclude our deep dive into magnetars, we stand ready to zoom outward by a factor of 1 billion or more. The lessons learned about magnetic fields contending with matter, about rotation and energy extraction, about bursts and beams of radiation, will accompany us. The magnetar has shown us magnetism's might on the small stage. Now, ahead lies the spectacle of quasars, where magnetic engines light up entire galaxies. The story continues, from the ultra-dense heart of a dead star to the swirling environs of supermassive black holes. Magnetars have been our guides to the frontier of physics. Carrying that knowledge, we venture next into the realm of quasars to see how the cosmos wields those same forces on scales that defy imagination, and to discover what new mysteries await among the most extreme galactic engines of all. In the depths of space, a new kind of cosmic marvel awaits us. We leave behind the crackling magnetism of neutron stars and drift toward the realm of unimaginable light. Gently, we arrive at the doorstep of quasars, beacons so distant and bright that they defy common understanding. These are the quasi-stellar enigmas that puzzled astronomers, appearing as tiny star-like points in the sky, yet shining with a power beyond any star. Their photons have travelled billions of years across expanding space to reach our telescopes, making quasars not only bright, but also ancient beacons from a younger universe. In the mid-20th century, radio telescopes began picking up mysterious signals from the far reaches of the universe. Astronomers found intense sources of radio waves that had no clear counterparts in visible light. No obvious galaxies or nebulae, just faint, star-like specks. They named them quasi-stellar radio sources because in early photographs they resembled dim stars. Yet something was odd. When scientists split their light into spectra, the usual patterns of atomic lines were shifted and strange. For a time, nobody could recognize the chemical fingerprints. It was as if these objects were made of elements unknown, deepening the mystery around these cosmic beacons. One of these enigmatic radio sources, labeled 3C273, offered a crucial clue in the early 1960s. Astronomers watched as the moon, gliding through the sky, passed in front of 3C273 and caused its radio signal to wink out momentarily. Using this lunar occultation, they pinpointed the source's position in the sky and discovered a faint, star-like speck of light at that exact spot. At long last, the mysterious signal had an identifiable counterpart in visible light. It was a modest-looking object, but it held the key to solving the quasar puzzle. Soon after, a detailed look at the light from 3C273 provided the answer. An astronomer noticed that the jumbled spectral lines made sense if they were actually familiar elements, mainly hydrogen, shifted far toward the red end of the spectrum. Such an extreme redshift meant that 3C273 was incredibly far away, billions of light-years from Earth. This realization was staggering. If that tiny point of light was so distant, then to appear as bright as it did, it must be unleashing more light than entire galaxies. The object seemed to shine with the light of trillions of suns, a beacon from the edge of the observable universe. Word of this discovery spread, turning scientific bewilderment into awe. Soon, these objects were given a shorter name, quasars, a contraction of quasi-stellar radio sources. At first, many found it hard to accept that something so small-looking could be so far away. The idea challenged comfort zones, implying energies on a scale never seen before. But observation after observation confirmed high redshifts for other quasars scattered across the sky. Each was a puzzle piece pointing to a profound truth. These were not lone stars at all, but the brilliant cores of distant galaxies in an active, fiery state. It turned out that quasars were an extreme version of a phenomenon already occurring in some galaxies. In the 1940s, astronomers had noted a few nearby galaxies with unusually bright cores, later called Seyfert galaxies, but nothing prepared them for the sheer power of quasars. Gradually, a picture emerged of what quasars truly are. They reside in the hearts of young galaxies, so luminous that their glow drowns out the combined light of billions of surrounding stars. Astronomers realized they were seeing the intensely energetic centers of galaxies, what we now call active galactic nuclei. In nearby galaxies, weaker active nuclei had been observed in Seyferts, but quasars were the most extreme incarnation of this phenomenon. The term active galactic nucleus, or AGN, became the key. A quasar is essentially an AGN on overdrive, a galactic core radiating ferociously as it devours matter. The big question remained: what could possibly power such brilliance? The answer pointed towards something long considered almost mythical: supermassive black holes. For decades, black holes had been theoretical curiosities, solutions to equations that seemed too strange to exist in reality. Yet here, in quasars, nature was offering evidence that supermassive black holes not only exist, but also serve as cosmic engines. The only mechanism scientists could fathom to produce quasar-level energy was matter plunging into a giant black hole, releasing vast energy in the process. Thus, quasars became the first convincing proof that supermassive black holes are real. These distant beacons transformed an abstract idea into tangible reality, revealing that at the center of each quasar's host galaxy lurks a black hole millions or billions of times the Sun's mass. This revelation gave black hole physics a jolt. No longer were such dark objects just theoretical novelties, but necessary actors on the cosmic stage. The discovery of quasars inspired new efforts to understand how nature could produce and grow these monstrous black holes, tying the fate of galaxies to the deep predictions of general relativity. With this insight, the once bewildering quasi-stellar objects fell into place within the cosmic order. No longer were they oddities without context. They were the flamboyant adolescence of galaxies, a phase when a galaxy's core lights up the cosmos. The discovery of quasars was a watershed moment, connecting the dots between faint smudges of light and the most powerful engines in the universe. It opened our eyes to an active universe, one where galaxies themselves can shine like stars in the night, thanks to the maelstrom in their nuclei. And as one mystery resolved, a new journey began, to understand the anatomy of these engines of light and how they produce such astounding luminosity. Through these discoveries, what was once a puzzling point of light became a bridge to understanding the darkest objects in the cosmos. Now, with the mystery of their identity solved, our gaze turns inward to the heart of a quasar. Within that tiny point of light lies a whole drama of gravity and energy. How does a supermassive black hole, an object that emits no light of its own, create one of the brightest lights in existence? In the next moments, we drift closer to explore the glowing accretion disk and the furious furnace of gravity that fuels a quasar's radiance. We descend into the glowing whirlpool that surrounds the black hole, a structure known as the accretion disk. Here, gravity's pull has gathered a swirling disk of gas and dust spiraling ever inward. In this disk, matter crowds together and rubs against itself under tremendous forces, heating up as it falls. The gas glows brilliantly, transforming gravitational pull into light. We have entered the gravity furnace, a place where the energy of infalling matter is released in an incandescent torrent. Even though the central black hole itself remains dark, hidden behind an event horizon beyond which not even light can escape, the material around it shines as bright as 1,000 galaxies, powered by the irresistible attraction at its core. It is a mesmerizing process, gravity crafting light from darkness, forging brilliance in the very act of cosmic infall. This accretion disk is a masterpiece of extreme physics. As gas spirals toward the black hole, it moves faster and faster, whipping around in orbits at nearly the speed of light near the center. The friction and compression in the disk raise the temperature to extraordinary heights. The innermost regions blaze in ultraviolet light and even soft X-rays, while the outer parts, slightly cooler, radiate in visible and infrared hues. If we could hover above this cosmic maelstrom, we would see a great disk fading from a searing bluish white at the center to a dimmer red glow further out. It is like a cosmic hurricane of glowing gas, with the black hole hidden in its eye, quietly driving the fury around it. Remarkably, the entire accretion disk might span only a few light days in radius, comparable to the size of our solar system. Yet it outshines galaxies that are thousands of times larger. The efficiency of this process is astonishing. In the core of a star, only a tiny fraction of mass is converted into energy through nuclear fusion. But in a quasar's accretion disk, gravity wrings vastly more energy from matter. As matter falls inward, Each step deeper into the gravitational well releases energy, much of which emerges as heat and light. In fact, a few kilograms of gas consumed by the black hole each second can outshine entire clusters of stars. A single raindrop of mass, in cosmic terms, lights up the universe when it falls into this gravitational furnace. This makes the quasar's engine far more potent than any star's core. It is as if nature has found a way to turn matter almost directly into pure radiance. To put it another way, black holes are the ultimate power plants. A quasar's disk can convert around 10% or more of the mass it devours into energy, whereas the sun fuses hydrogen into helium at less than 1% efficiency. That means dropping a lump of matter into a black hole can release up to 10 times more energy than detonating that mass in the core of a star. This incredible efficiency is why quasars shine so fiercely. A modest amount of infalling gas, say a few solar masses per year, can produce luminosity that dwarfs an entire galaxy of billions of suns. It is an almost alchemical transformation, mass into light, driven by gravity. Yet there are limits, even for a quasar's brilliance. As the disk churns out light, the pressure of that intense radiation pushes back on the infalling gas. If too much matter tries to fall in at once, the quasar's own luminosity acts like a forceful wind, blowing material away and throttling the feast. The black hole is powerful, but it cannot swallow infinite amounts without protest from the light it unleashes. Thus, each quasar likely finds a balance, a point where gravity, pulling in, and radiation pushing out reach equilibrium. Even in this, there is a grace to the violence. The quasar self-regulates, preventing its engine from burning too hot for too long. At roughly a few light years out, the quasar's glare finally weakens enough for dust grains to survive without being vaporized. Surrounding the brilliant disk is darkness, punctuated by the glow of that radiant whirl. Floating just above the disk's luminous frenzy is an elusive halo of superheated particles, the quasar's corona. This tenuous shroud of electrons, heated to extraordinary temperatures, wraps around the inner disk and produces a new kind of light. In the corona, the energy from the disk's glow is boosted even further, driving photons to X-ray energies. It is a nearly invisible veil, seen only by the powerful X-rays it pours into space. In truth, the corona's exact structure remains puzzling, and scientists continue to probe its secrets. It might consist of magnetically confined plasma loops or arches rising above the disk, akin to the sun's corona, but on a vastly greater scale. On occasion, those magnetic fields may snap and realign, unleashing sudden X-ray flares, a titanic version of the sun's solar flares, briefly boosting the corona's glow even further. Within this halo, a remarkable transformation occurs. Photons that pour out of the accretion disk, mostly ultraviolet and visible light, find themselves racing through a swarm of energetic electrons in the corona. When a photon collides with one of these electrons, it gains a surge of energy, like a small boat riding the wake of a fast ship. With each encounter, the photon's wavelength shortens and its energy climbs. A gentle UV photon can emerge from the corona as a powerful X-ray after being scattered by these hot electrons. This process, known as Compton upscattering, is nature's way of taking the quasar's low-energy light and boosting it into high-energy brilliance. Billions of such upscattered photons escape the corona each second, carrying away a record of this extreme zone. The X-ray glow of a quasar's corona adds a new dimension to its power. These X-rays are even more penetrating and energetic than the light from the disk. If one could see the sky in X-ray vision, quasars would stand out as flickering beacons across the cosmos. In fact, astronomers do observe quasars with space-based X-ray telescopes, and they notice that this high-energy emission can vary rapidly. The corona often flickers on timescales of days or even hours, hinting that it is a compact region, not much larger than the black hole's shadow itself. Such rapid variability tells us the X-ray emitting region is extremely small, no wider than a few light hours or light days at most, since a larger area could not change brightness so quickly. In those swift changes, we can almost sense the frantic dance of particles and fields near the edge of the abyss. Though we cannot see the corona directly, its X-ray fingerprints tell a story. Some of the X-rays shine down onto the accretion disk below, illuminating it in high energies and casting fleeting shadows where dense gas blocks the way. By studying these reflections, scientists learn about the disk's inner edge and even gauge the spin of the black hole. Other X-rays stream outward into space, traveling for eons across the universe. X-rays from quasars have been detected billions of light-years away, a testament to the sheer intensity of this process. They carry with them clues about conditions near the black hole, acting as messengers from a realm of extreme gravity and temperature. The corona is a reminder that even unseen forces can leave a powerful imprint, bathing the surroundings in a high-energy glow. From the brilliant central disk and its X-ray crown, the quasar's light does not stop. It races further out and encounters new territory. The surrounding gas and clouds that swirl through the host galaxy's central regions. Bathed in the intense radiation from the core, these clouds respond like a cosmic choir to a conductor's baton, each emitting its own spectral lines in answer to the quasar's song. We drift outward now, leaving behind the blinding glare of the inner X-ray realm, and enter a region of swirling interstellar clouds. Here, the story of the quasar continues in the motions and lights of gas clouds orbiting the central black hole, revealing the next layer of the quasar's anatomy. We find ourselves amid a vast assembly of gas clouds surrounding the quasar's core. The brilliance from the center shines upon these interstellar mists, causing them to glow in a variety of colors. Each cloud is like a lantern lit by the quasar's light, and together they form a luminous nebula enveloping the black hole region. But these lights are not static. Each cloud is in rapid motion, orbiting under the black hole's gravitational spell. Some race through this inner region at thousands of kilometers per second, a few % of the speed of light, while others drift more leisurely farther out. The result is a beautiful chaos, a dynamic system of clouds in motion, each leaving its signature in the quasar's spectrum. Closer to the black hole is a chaotic swarm of gas moving at incredible speeds. These inner clouds, so close in, whip around the black hole in tight orbits, creating broad smears in the light they emit. When astronomers look at the spectrum of a quasar, they see certain bright emission lines, fingerprints of elements like hydrogen or carbon, stretched wide across wavelengths. This broadening is due to the Doppler effect. Some clouds are rushing toward us, others away, so their light is shifted to bluer or redder wavelengths. All those shifts blend together into broad, fuzzy, spectral lines. This zone of high-speed clouds is appropriately named the broad line region. It spans a relatively small volume, perhaps only a few light days or weeks across, yet it is packed with gas, hurtling unpredictably under gravity's dominion. In contrast, if our view is aligned above or below this plane, we peer down the funnel of the dusty donut and directly see the dazzling core. Aligned face on, none of the central light is hidden, and the object appears to us as a full-fledged quasar in all its glory. Farther out from the centre, beyond the tumult of the broad line region, lies a calmer expanse of diffuse gas. Here, the gravitational grip is weaker, and clouds orbit more slowly, tens or hundreds of kilometers per second instead of thousands. The emission lines produced by this distant gas remain narrow and sharp, since the Doppler shifts are much smaller. We see the same elements glowing, but now their spectral lines are thin, distinct peaks. This outer zone is called the narrow line region, extending across light years of space. It can reach into the host galaxy itself, blending with the surrounding interstellar medium. In some quasars, these narrow line clouds form conical outflows, or vast, glowing filaments stretching away from the nucleus. Though dimmer than the furious inner region, the narrow line clouds still shine with the quasar's reflected power, serving as a bridge between the extreme core and the wider galaxy. One of the remarkable things about these glowing clouds is how they respond to changes in the quasar's light. The energy from the accretion disk can fluctuate, brightening or dimming as the black hole's feeding rate varies. When the central beacon flashes brighter, the inner clouds soon intensify their glow. When the beacon fades, the cloud's light diminishes as well. But there's a delay in their response, a lag corresponding to the time light takes to travel from the quasar's core out to the clouds. Astronomers have learned to use this delay as a tool in a technique known as reverberation mapping. By monitoring the quasar's core brightness and the subsequent echo of light in the broad line clouds, they can determine the distance to those clouds. For example, if a burst of light from the center is observed and a particular emission line brightens 2 weeks later, we know the gas producing that line lies 2 light weeks away. The principle is akin to judging the distance of a storm by the delay between lightning and thunder. A flash of light followed by a later boom reveals how far the storm clouds are. Similarly, by timing the quasar's thunder in the orbiting gas, we gauge how far those clouds lie from the central source. These light echoes allow us to create a cosmic map of the quasar's inner regions, even though they are far too small to image directly. By combining the measured distance of the clouds with their speeds, gleaned from the width of their spectral lines, scientists can even weigh the central black hole. A cloud orbiting swiftly at a known distance must be held by a certain mass. Using the laws of gravity, the calculations reveal a black hole's mass as millions or billions of suns. Through these echoes and motions, the quasar divulges its secrets. It's as if we are using interstellar sonar to probe an invisible structure. We begin to see a layered architecture. At the core, a tiny disk and black hole. Around it, a shell of rushing clouds. Beyond that, gentler clouds merging into the galaxy itself. All of it orchestrated by gravity and illuminated by the central light. By listening to these light echoes, astronomers turn flickers into a map, unveiling structures far too small to observe directly. As we drift in this realm of glowing clouds, we notice that not all of the quasar's light escapes freely into space. In certain directions, something obscures our view toward the core, as if a curtain has been drawn across the brilliant stage. A dense band of darkness and dust lurks further out, girdling the quasar. To truly understand the quasar's appearance from every angle, we must confront this obscuring structure. Gently, our journey carries us outward, into the embrace of this dusty veil that encircles the quasar's central light. Out beyond the glowing clouds, the quasar is encircled by a thick, obscuring belt of dust and gas. It is as though the heart of the galaxy wears a dark veil, a cosmic shawl wrapped around the bright core. This structure is often envisioned as a torus, a donut-shaped ring of material orbiting a few light years from the black hole. Within this torus, countless grains of cosmic dust swirl in orbit, dense enough to block the intense light coming from the inner regions. Peering through this zone along the galaxy's equator, one would see very little of the quasar's gleam. The central engine would be hidden behind a haze of its own exhaust. This dusty veil plays a crucial role in how we perceive quasars from afar. If we, as observers, happen to view a quasar edge-on, meaning through the plane of this dust ring, the brilliant inner light is mostly obscured. The quasar's broad-line clouds and accretion disk might be completely out of sight, cloaked by dust. All we might detect are hints of its presence, perhaps some narrow emission lines leaking out above the dust, or the faint glow of scattered light. Such an obscured quasar might not look like a classic beacon at all. It could masquerade as a relatively dim galaxy with an unusual spectrum. In contrast, if our view is aligned above or below the torus, we peer directly down its central opening and behold the dazzling core. In that orientation, none of the quasar's central glow is hidden, and the object reveals itself as a full-fledged quasar in all its glory. The dust in the torus is not merely an absorber of light, it also re-emits that energy in other forms. The intense radiation from the quasar's center heats the dust grains to high temperatures, though still far cooler than a star's surface. As a result, the torus glows brightly in infrared light, like warm embers encircling a fire. Astronomers searching the skies in infrared can spot this telltale sign. An otherwise modest-looking galaxy, shining unexpectedly at infrared wavelengths, betraying a powerful hidden quasar at its core. In this way, even when a quasar hides behind its dusty curtain, we can sense its presence through the heat leaking out. In some cases, however, a few penetrating X-rays or radio waves can leak through the dust as well, hinting at the powerful engine concealed within.
Realizing the importance of orientation led astronomers to a profound insight, often called the unification model of active galaxies. Many objects that once seemed different, quasars, radio galaxies, Seyfert galaxies, are now understood as fundamentally the same central engine viewed from different angles. The dusty torus is key to this unity. When the central engine is visible, we see a quasar, or a blinding active nucleus, with broad lines and fierce light. When it's edge-on and hidden, we see only a fraction of its power. Narrower lines, a weaker glow, perhaps just radio or X-ray whispers penetrating the dust. But underneath, it's the same engine. This concept brought order to what had been a zoo of active galaxies, revealing that a single structure, black hole, disk, corona, clouds, and torus, can wear many disguises depending on how we happen to view it. Drifting along the outskirts of this dusty ring, we see that it forms a boundary between the quasar's inner sanctum and the rest of the galaxy. Through gaps above the torus, some of the quasar's light and energy escape freely into space, beaming out along the axis of rotation. And along with that escaping light, something else emerges. Jets of charged particles shooting out in opposite directions, perpendicular to the plane of the torus. These jets spear through the surrounding space, unimpeded by dust, carrying the quasar's influence far beyond its host galaxy. Our journey now turns to examine these spectacular cosmic jets and beams, columns of plasma propelled at near light speed that serve as the quasar's far-reaching emissaries into the cosmos. Not all quasars are content to radiate their energy as light alone. In some of them, the fury of the central engine is channeled into twin jets of plasma that erupt from the poles of the accretion disk. These jets are like cosmic fire hoses, launching streams of charged particles at velocities close to the speed of light. They pierce through the surrounding galaxy and beyond,
carving a path deep into intergalactic space. Spiraling along invisible magnetic field lines, the charged particles emit radio waves and visible light as they whip outward, turning the jets into brilliant beacons that can stretch for hundreds of thousands of light years. It's as if the quasar has drilled two narrow tunnels through its environment, sending tremendous energy outward in focused beams. Quasars with such mighty jets are known as radio-loud quasars, named for their prodigious radio wave output. Early radio astronomers discovered some galaxies that appeared quiet in visible light, but had giant lobes of radio emission blooming on either side. Only later did we realize these were powered by quasar-like cores shooting out jets. At the ends of the jets, enormous radio lobes inflate where the jets ram into the tenuous intergalactic gas, like cosmic sonic booms lighting up the void. The entire structure can dwarf the host galaxy, reaching far beyond it. In optical light, the host galaxy might look unremarkable, but in radio waves, it reveals this colossal double-jetted anatomy. This is the signature of a radio-loud quasar. Not only a bright central engine, but also machinery that launches matter across unimaginable distances. Perhaps the most dramatic case is when one of these jets points almost directly toward Earth. Because we are nearly in its line of fire, the quasar's emission is intensified by relativistic effects. Its light is beamed in our direction, and time appears to run faster for its flickering signals. We call such an object a blazar. Blazars present as wildly variable sources. Their brightness can surge or drop in a matter of days, and they emit fiercely across the spectrum, from radio waves to gamma rays. In a blazar, we are essentially staring down the barrel of the jet. Every pulse of energy, every twist of magnetic field near the black hole is broadcast to us in amplified form. These are among the most erratic and luminous objects known, and they underscore how much orientation matters. The same quasar, if viewed from the side, might appear as a relatively calm radio galaxy, with its central drama hidden from direct view. In such cases, the jet's incredible speed can even play tricks with light. Blobs of plasma racing outward can seem to move faster than light itself when observed from Earth. A mind-bending illusion created by their near-light velocity and the angle of the jet toward us. Of course, nothing truly exceeds the speed of light. This superluminal motion is a consequence of light travel times and projection effects. But it powerfully demonstrates just how close to nature's ultimate speed limit these outflows are. Scientists believe that the engines of these jets are the spinning black hole and its accretion disk acting in concert. The rapid rotation of a supermassive black hole, combined with intense magnetic fields in the swirling disk, can act like a giant dynamo. This process extracts energy from the black hole's spin and channels it into accelerating particles outward. The result is a pair of relativistic outflows carrying matter and energy away from the quasar. In some cases, we even observe an optical jet streaking out from a quasar's core, a faint pencil of bluish light on images, marking where electrons moving at near light speed emit visible radiation. Such observations confirm that we are witnessing particles pushed to incredible velocities, guided by magnetic forces rooted deep in the quasar's heart. The impact of these jets extends beyond visual spectacle. As they plough through the galaxy's halo and into intergalactic space, they heat and stir the tenuous gas they encounter. A powerful quasar jet can deliver energy to the outskirts of its galaxy, and even beyond, possibly suppressing or triggering new star formation by the way it agitates gas clouds. Thus, the quasar's influence can extend far beyond its immediate vicinity. connecting the fate of the central black hole with the evolution of the entire galaxy. We see in jets another facet of the quasar's extreme nature. Not only do quasars shine brilliantly and stir their local space with radiation, they can also physically shape their cosmic surroundings through these high-speed outflows. Astronomers have observed, for example, that some clusters of galaxies contain gigantic bubble-shaped cavities in their hot gas, clear imprints of ancient quasar jets that pushed the gas aside, injecting energy on scales of hundreds of thousands of light-years. Such jets illustrate how a quasar's influence can extend well beyond its host galaxy, connecting an entire cluster of galaxies with its energy. Amidst this spectacle of light and jets, we are reminded that none of it would exist without fuel. All the radiance of the accretion disk and the power of the jets depend on a steady diet of matter falling into the black hole. If that supply falters, the quasar will quiet down, its lights dimming and its jets weakening. How, then, does a galaxy feed such a monster at its heart? Our journey now widens its scope to the larger galactic environment. We will watch how galaxies themselves provide infalling gas to their central black holes, and how quasars flicker on and off over cosmic time as their fuel comes and goes. It is time to explore the life cycle of quasars, how they are fueled, how long they burn, and what can set them alight in the first place. We zoom out to the scale of an entire galaxy now, to witness how such a magnificent but voracious quasar is sustained. A supermassive black hole, even 1 billions of times the Sun's mass, is tiny compared to a galaxy. It sits at the center, like a demanding seed that needs nourishment. Fuel for that seed comes in the form of gas, and sometimes even stars, funneling down into the core. But under normal conditions, much of a galaxy's gas remains in orbit, far from the center, forming stars or simply meandering in the galactic disk. To wake up a quasar, something must disturb this equilibrium and send a fresh surge of matter toward the waiting black hole. One of the most dramatic triggers for quasar activity is a galactic merger. Imagine two galaxies drawing near, their mutual gravity throwing stars and gas into disarray. In the slow, colossal dance of a merger, tidal forces channel great rivers of interstellar gas inward. Like tributaries feeding a central lake, these streams flow toward the nucleus of the newly forming galaxy. As the two galaxies coalesce, their central black holes may eventually join as well. But long before that, the inflowing gas collects around one or both of them, forming a rejuvenated accretion disk. This influx of fuel ignites the quasar, making the galactic core blaze amid the chaos of the merging galaxies. Many of the brightest quasars observed in the universe are found in galaxies that bear the scars of recent collisions, distorted shapes, long tidal tails of stars flung outward, and other hallmarks of cosmic upheaval. The violence of a merger provides a banquet of gas for the central black hole, and in return, the quasar lights up with furious energy. Mergers are not the only way to feed a quasar. Even in solitary galaxies, internal structures can gradually channel gas inward over time. Consider a spiral galaxy with a bar, an elongated concentration of stars across its center. This bar acts like a gravitational paddle, stirring the galaxy's gas and directing it toward the nucleus. Over tens or hundreds of millions of years, such processes can deliver enough matter to awaken a modest active nucleus at the galaxy's core. The result might be a weaker cousin of a quasar, perhaps a Seyfert galaxy with a brilliant core, or a low-level AGN quietly shining in an otherwise normal galaxy. Still, Given enough time and accumulated gas, even a relatively quiet galaxy can flare into quasar-like brilliance. Sometimes, a minor interaction, a glancing pass by a smaller galaxy, or the accretion of a giant gas cloud, can trigger a feeding event. The black hole is patient, waiting for any opportunity when gravity can funnel material into its grasp. When a quasar does turn on, it doesn't necessarily burn steadily forever. Instead, quasar activity is often episodic. A single feeding event might make the quasar shine brilliantly for several million or even tens of millions of years. A brief flash by cosmic standards. As the black hole feasts, it may also sow the seeds of its own starvation. The intense radiation from the quasar, along with the force of its jets and winds, can blast much of the remaining gas out of the galaxy's center. In effect, the quasar can blow away its own fuel supply. Eventually, the inflow of gas slows to a trickle. The accretion disk thins, the broad-line clouds dim, and the once blazing nucleus fades into relative dormancy. The black hole remains, but without a bright disk, it becomes a dark, silent heavyweight at the galaxy's core. This on and off pattern is sometimes called the duty cycle of quasar life. A galaxy's central black hole might spend only a small fraction of its time shining as a luminous quasar. In the afterglow of a feeding frenzy, eons can pass while the monster lies in wait again. Then, perhaps through another merger or a fresh infall of gas, the engine roars back to life. Each galaxy likely experiences multiple such awakenings across its history. Our own Milky Way's quiet center, for instance, shows hints of past activity. Vast bubble-shaped outflows detected in high-energy light suggest that a few million years ago, our central black hole gulped down a hefty meal and belched energy into the galactic halo. If so, even a relatively gentle galaxy like ours can, under the right conditions, stir to quasar-like life for a time. Over cosmic time, these intermittent quasar episodes have profound consequences. Each active phase can heat and expel gas, affecting the future of star formation in the host galaxy. Galaxies and their quasars seem to co-evolve. As the galaxy grows and changes, so does its black hole, each influencing the other. When quasar winds expel the last fuel, they often quench star formation in the host galaxy. A once gas-rich galaxy can then evolve into a more quiescent elliptical system, its central black hole left dormant amid aging stars. In young galaxies with ample gas, quasars flare often, shaping the galaxy's development. In older, gas-poor galaxies, the quasar sleeps, having already consumed or driven out most available fuel. To truly understand quasars, we must now step back further, into the grand timeline of the universe itself. When were quasars most common? How did the first quasars arise in the dawn of time, and what role did they play in the early cosmos? Our journey shifts to a cosmic historical perspective, tracing quasars through time, from their primordial origins to their golden age, and onward to the quieter present, where only echoes of that brilliance remain. In time, even the mightiest quasar must yield to calm, but its memory lives on in the changed galaxy it leaves behind. The tale of quasars is also a story about time. To truly appreciate their significance, we gaze deep into the past, when the universe was young and quasars were just beginning to flicker to life. In the cosmic dawn, only a few 100 million years after the Big Bang, the first stars and galaxies were taking shape. Amidst those early structures, the seeds of quasars were planted. Some were the remnants of the very first generation of massive stars. Stars that lived fast and died in colossal supernovae, leaving behind black holes a few tens of times the Sun's mass. Others might have arisen more directly. Under rare conditions, an entire cloud of primordial hydrogen could collapse straight into a black hole, skipping the usual star phase and creating a black hole seed of perhaps 100,000 solar masses. In either case, these seeds, tiny by quasar standards, began to grow. By feeding on infalling gas in those protogalaxies, and sometimes merging with one another, these nascent black holes gained mass. Remarkably, within a few 100 million years, some black holes swelled to enormous size, over 1 billion times the mass of our Sun, allowing the first true quasars to ignite. By around 700 million years after the universe began, quasars were already painting the darkness with light. Astronomers have discovered quasars from this epoch, tiny points of brilliance in the young universe, whose light has travelled more than 13 billion years to reach us. These infant quasars tell us that even in those early times, some young galaxies could create and fuel supermassive black holes. These early quasars likely played a role in a pivotal cosmic transition, the reionization of the universe. After the Big Bang, the cosmos was filled with neutral hydrogen gas, a fog that made space opaque to ultraviolet light. The intense ultraviolet glare of the first stars and quasars began to lift that fog, ionizing the hydrogen and turning the lights back on in the cosmic theatre. By about 1 billion years into cosmic time, this process had cleared most of the primordial haze, making the universe largely transparent. Each early quasar was like a miniature cosmic sunrise, clearing out a bubble of clarity in the gloom. If we could have watched the sky of that epoch, we would have seen darkness gradually giving way. The once opaque cosmos became a patchwork of growing bubbles of light, as islands of stars and nascent quasars turned the cosmic night into a new dawn. As time marched on, quasars became more numerous and even more powerful. Galaxies continued to collide and grow, feeding their central black holes. There came a period often referred to as the cosmic noon of quasars, the epoch roughly 10 to 12 billion years ago, when quasar activity across the universe peaked. During this era, the universe was in its vigorous teenage years, so to speak. Countless galaxies were actively forming stars at high rates, and many harboured blazing quasars at their cores. The night sky of that epoch, had there been any observers to witness it, would have been speckled with the glow of active galactic nuclei in every direction. Quasars were more common than at any other time, each one a beacon of creation and destruction. It was the golden age of quasar growth. Supermassive black holes were guzzling gas, shining furiously, and driving winds and jets that shaped their surroundings. After this peak, a slow decline set in. The universe expanded and evolved. Gas within galaxies grew scarcer or became locked away in stars. Major mergers became less frequent. One by one, the great quasars began to wane as their fuel sources dwindled. By about 5 or 6 billion years ago, the quasar population had thinned significantly. The cosmos transitioned into a quieter afternoon and eventually evening in terms of galactic activity. Star formation rates dropped, and many galaxies settled into a more quiescent state. In today's universe, quasars are comparatively rare. We find them mostly at great distances, their light coming to us from a youthful past. Nearby galaxies typically house only the dormant remnants of those quasar glory days. Massive black holes that are quiet, remembered only by the subtle effects of their gravity or faint echoes of past activity. Now and then, a galaxy in our neighbourhood will exhibit a modest flare of activity, Perhaps a minor accretion event causes our Milky Way's core to brighten slightly, or a relatively faint AGN blinks in a distant galaxy. But these are mere embers compared to the bonfires of the quasar epoch. Yet the story is not quite over. Even in a matured universe, echoes of those wild quasar days remain. Occasionally, a galaxy's central black hole will indulge in a small snack, a cloud of gas wandering too close, and the core will flicker to life in a scaled-down imitation of a quasar. With sensitive instruments, we can detect the subtle glow of material accreting onto central black holes in many galaxies, so-called active galactic nuclei, though they are feeble embers next to the quasars of old. Every massive galaxy's core tells a tale. The larger the galaxy's central bulge, the more massive the sleeping black hole within, hinting at their entwined growth over time. The relationship forged in the universe's youth persists, imprinted in the present-day cosmos. Meanwhile, new observational tools continue to push our knowledge. The James Webb Space Telescope and other advanced observatories are now peering into those early times, uncovering active black holes in infant galaxies and extending our view closer to the birth of the first quasars. Each new discovery of a distant quasar is like a message in a bottle from a younger universe, helping us piece together how these cosmic Goliaths came to be. Looking across the eons, we see a life cycle. Quasars were born in the universe's youth, flourished in its middle age, and then faded as the cosmos matured. Theirs is a story of light and change on the grandest scales. It is also a story of extremes, a testament to how nature, given the right conditions, pushes physics to its limits, whether in the ultra-intense magnetic fields of a magnetar or the voracious gravitational feeding of a quasar. Through the window of deep time, quasars have illuminated not just their host galaxies, but the very history of our universe. And though the era of great quasars is mostly behind us, their glow still reaches us, and their legacy lives on in the quiescent giants at the centers of galaxies everywhere. Quasars, once the universe's lighthouses, now guide our understanding of cosmic evolution across billions of years. Our journey through magnetars and quasars, these two extremes of scale and energy, has revealed some of the most astonishing behaviors matter can exhibit under the laws of physics. From the crackling magnetic fields of collapsed stars to the blazing accretion disks of galaxy-spanning beacons, we have witnessed nature at its most extreme. As we prepare to leave the realm of these cosmic marvels, we carry with us a renewed sense of wonder. The universe has many stories, and those of magnetars and quasars are among the most dramatic. In our final reflections, we will ponder what these exotic objects teach us about the cosmos, and how they inspire us to continue exploring the mysteries of space and time.